So we're moving on to differential equations. And I remind you, this is going to be quite a big topic. So we're going to start this week, but we're going to carry on for a few weeks on differential equations. So we're going to start off just by recapping a little bit of our A-level maths. So just check that you know how to integrate different things. So if I were to ask you to integrate cot x, you probably know what the answer is, or you might have forgotten the integral of cot x, but it is something that you should try and remember. So the integral of sec x and the integral of cot x are ones that, well, you can work them out even if you've forgotten them, but it's better off just remembering them. So do you know the integral of cot x to Shane?
Yes, learn mod sine x.
Learn modulus of sine x. Lovely. If you didn't know, you'd rewrite it as cot x is cos x over sine x. And then you'd say, oh, what's my guess going to be? And you'd say, my guess is going to be ln of sine x. And when you differentiate ln of sine x, it gives you cos x over sine x. And it works perfectly. So your guess was correct. So everything is nice and easy and straightforward. Okay, what about the integral of sec x? What's the integral of sec x? Integral of sec x, that's one you really have to remember. You can't just quickly work that one out. You just kind of need to remember it. Shruti?
Learn mod of tan x plus
sec x plus tan x.
Sec x. Yeah.
Ln of modulus of sec x plus tan x. Again, that's one we learn, and now you should just remember it. Okay, so I want to integrate this one here. How would I integrate that? What would my guess be? And then what would my answer be? Joe?
Would your guess be ln 1 minus 3x?
Yeah, but 1 minus 3x would give me minus 3 over 1 minus 3x when I differentiate it. You've got 2 here.
So then the adjustment would be minus 2 over 3.
Perfect, good. Minus 2 over 3. Okay, next one, this one here. What's this integral here? Het. What's your guess going to be?
So your guess would be x1 plus x cubed, all learned.
Ln of modulus of 1 plus x cubed. And then when you differentiate, that gives you?
That differentiated would give you 1 over 3x squared.
When you differentiate ln of something, you get 1 over the same thing. So ln of 1 plus x cubed gives you 1 over 1 plus x cubed.
1 over x.
But you have to
differentiate the inside of it as well. So it'd be x cubed, 3x squared, yeah.
And that's not right because we want x squared. We don't want 3x.
So it would be a third in front of it, wouldn't it?
Okay, yeah. Okay, so there's our answer for that one. So we know how to do these sort of integrals. They're pretty straightforward. Okay, one more. What about this one here? And I've highlighted that one with a red dotted line around it. So there's something important about this one. Integral of f dashed x over fx. So I'll give you an example. F dashed x over fx could be, it could be 3x squared over 1 plus x cubed. For instance, if that was f of x, then that is the differential of it. So it would be f dash x. I'll give you another example. If we had cos x over sine x, then if that was fx, then that would be f dashed of x. Differential of sine x is cos x. Differential of 1 plus x cubed is 3x squared. What's the integral of this? What's the integral of this? And therefore, by deduction, what is the integral of this? Devonch? 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 Can you hear me, Devonch? Just nod. Oh, your mic isn't working. Okay. What's the answer, Shruti? It's not hard. Look, what would this one be? Integral of 3x squared over 1 plus x cubed. What would your guess be? Remember, you got your mic off, yeah?
Sorry. So it's the ln of the bottom.
Ln of the
part.
bottom. So what's
Yeah.
this one?
Oh, ln of fx.
Okay.
And times.
Well, you don't need to times
Times
by anything because it works perfectly because you've got exactly f dash x on the bottom, on the top of the
okay.
But so the answer is ln of f of x is the answer, ln of modulus of f of x. We're going to come across this later on in the lesson today. So when we get integral of f dashed x over fx later on in the lesson today, I want you to all shout out ln of f of x, ln of f of x. Just shout it out. Don't worry about waiting for me to say anything. Just shout it out. Yeah, all of you together in unison. Okay. There are some other ones that we might need to be able to integrate as well. We might need to be able to integrate things like this. If we wanted to integrate ln x, we would use parts to do that. We'd write it as integral of ln x times 1. And so we'd leave alone the first one, ln x, integrate the second one, x, minus integral of differentiate the first one, 1 over x, integrate the second one, x. That just gives you 1. And so it gives you x ln x minus x, integral of 1 of it is x. So the answer for that is x brackets ln x minus 1 is the integral of that. And then you've got other things like this where you just have to look at it and you have to say, oh, okay, well, what should my guess be here? And your guess might here just be ln x to the power 2. And the reason you would choose ln x to the power 2 is because the differential of ln x is 1 over x. And there is a 1 over x at the front of that. So you know that that guess is going to work. Okay, so that's just recapping the sort of integral stuff that we already know. Okay, now we're going to move, I'm going to ask you sort of slightly stranger questions. I'm going to tell you there's some function, and when you add that function to its differential, the answer is 3e to the 2x. So a function plus its differential gives you 3e to the 2x. What could you guess that the function was? And it really is just a bit of a guessing game at the moment. What could you guess that the function was? What might that function be that when you add the function to its differential, the answer gives you 3e to the 2x? It doesn't matter if you're right or wrong. We're just trying to see if we could try and guess the answer to this. Joe? Microphone?
Would it be e to the 2x plus e to the 2x?
Let's just do something simple. You said it could be e to the 2x, could be f of x, yeah? So we won't make it complicated first. So fx is e to the 2x. So then what would f dashed x be?
2e to the 2x.
Yeah, so e to the 2x plus 2e to the 2x would give you 3e to the 2x. So the answer is fx is e to the 2x. I think that's what you were trying to say anyway.
Yeah.
Okay, lovely, good. All right, let's try another one. So some function plus its differential gives you cos x. Some function plus its differential gives you cos x. And it doesn't matter if you're right or wrong. We're just going to start thinking about it. What might the function be? To Shane. Start off with anything.
So something to do with sine x.
Sine x, lovely. Sine x is going to be our f of x. And then our f dashed of x is going to be cos x. So sine x plus cos x. Okay, it's not going to give us cos x because when you differentiate a sine x, you get a cos x anyway. And so that's what's messed it up. So you might have to make this a bit more complicated than just sine x so that you can get rid of this extra cos x that we don't want. Oh, sorry, so that you can get rid of this extra sine x that we don't want, not the sine x. Not the cos x.
I'm not sure.
So you said sine x before, and we're trying to get the answer to be cos x. And at the moment, when you do fx is sine x plus f dash x, you get sine x plus cos x, which is kind of not right. We need to really get rid of the sine x. We just want the cos x. So your original guess was sine x. You need something that's going to differentiate to give you sine x so that you can get rid of the sine x.
So minus cos x.
So let's try sine x. Let's try sine x plus cos x as our guess. So let's start again. And this time our f of x is going to be sine x plus cos x. So sine x plus cos x is our f of x. In which case our f dashed of x is going to be differential of sine x is cos x, and differential of cos x is minus sine x, and we're adding them together. And so the sine x and the minus sine x cancel out, and it gives us, well, it gives us, it doesn't give us cos x, it gives us 2 cos x. Oh, crap. Is there an easy fix for that?
So you just half it.
Just halve it, just halve it. Okay, so there's our f of x. So there's our f of x is a half bracket sine x plus cos x. Okay, we want to try another one here. Again, we've got a function. We don't know what that function is. Plus its derivative is equal to x squared. Now, what happens with e to the x when you differentiate it is you just get more e to the x's. So when you differentiate an e to the x or an e to the 2x, you just get some more e to the 2x's. What happens with sine x and cos x is when you differentiate them, when you differentiate sine x, you get a cos x, and when you differentiate cos x, you get a sine x. So they don't immediately cancel each other out or add together. You end up with 2 separate terms. You end up with a sine x term and a cos x term. What happens when you differentiate polynomials like x to the 5? Well, it gives you an x to the 4. And what happens when you differentiate an x to the 4? Well, it gives you an x to the 3. It actually gives you 4x cubed, but I'm just interested in the type of term it gives you. So I wonder, what should our function be? And by this, I mean, what sort of form should our function be? Should it be a cubic? Should it be a quadratic? Should it be linear? Should it just be a number? Should it be an exponential? I can't see how it would be an exponential, but you might say that. So what form should our answer take such that f of x plus f dashed of x would be x squared? What form should it take? Should it be quadratic? Should it be linear? Should it be cubic? I'm asking that to Devansh. I'm not hearing you again.
Cubic, sir.
So what happens if you have a cubic here and you just leave it alone? Then what have you got so far?
You get x cubed.
A cubic would be just a cubic. So it's not necessarily just x cubed, but it could be like 5x.
It would be a cubic.
And what happens when you differentiate cubic? What does that give you?
Quadratic.
So you would have a cubic plus a quadratic. When you add a cubic to a quadratic, what is that? Is that going to be a quadratic, or is it going to be a cubic? Is it going to be a quartic?
It's going to be a cubic.
It is. So we don't want it to be a cubic. We want it to be a quadratic. So do you want to rethink that?
So f of x is probably going to be a quadratic then.
Quadratic. Now we don't know what it's going to be. So I'm going to suggest we call it ax plus b because we don't know what it's going to be. Yeah, and that's our general form for a, oh, sorry, no, you said quadratic. Sorry, let me just do that again. Said quadratic, so let's call it ax squared plus bx plus c. So that's our general form for a quadratic. So that's our f of x. Differentiate it, Devansh?
2ax plus b.
And then we need to add these together. So that's going to give us, let's change color. It's going to give us ax squared plus, these are the x terms, so b plus 2a lots of x. And then these are our units terms, plus b plus c. Now, what do you want a to be, Devansh?
1.
Yep, we want a to be 1. So we can say straight away, a's got to be 1. So we can put in a as 1. So if we know a is 1, then that's got to be 2. Okay, what do you want? How many x's do you want in your answer?
0. So b is going to be -2.
B is going to be -2. So I can change that to a -2 now. And how many units do you want in your answer?
0. So c is going to be 2.
So c is going to be 2. So therefore, according to what you said at the beginning, it should be 1x squared minus 2x plus 2. Let's check it. So that's our f of x. What's our f dashed of x?
2x minus 2.
2x minus 2. And if you add that whole lot up, what do you get?
You get x squared.
It works. Okay, it works. Okay, so what we did was we figured out what form it should be by knowing that when you have a quadratic and you differentiate it, you get a linear. And if you add a quadratic to a linear, that gives you still a quadratic. And so that told us that we must start with a quadratic to get a quadratic on this side here. What do you notice about the next question? What do you notice about the next question? Het.
The next question has a power of x to it.
Does have a power of x squared in it, but it doesn't just have a power of x squared in it.
I mean, it's got e to 2x in it as well.
3e to 2x and an x squared. Tell me what you notice again.
So it has to be quadratic. And
Tell me what you notice again.
That's got a power.
Okay, I'm trying to help you. Het.
Oh, it's the same as the above one, so it'd just be e to 2x and
Yeah, so these two terms, the 3e to the 2x and the x squared, these two terms that you see in this one here, they're two terms that we had from before. So I'm wondering, can we just add this answer here to this answer here? Well, the answer was that was the answer. I'm wondering, can we just add those two together? And of course you can, because differentiation is additive. So you can just add those two together. You can just say the answer is e to the 2x plus x squared minus 2x plus 2, and we've got our answer straight away. Okay, now the last one's going to get quite tricky. So we're not worried about it because we're going to learn how to do it in an easier way in a bit. So, but just tell me, so this is some function plus its derivative, and the answer has got to give us sort of 2x e to the x. So tell me what form you think the fx should be. Should it just be like e to the kx maybe? Or should it just be e to the x? You don't even need a k there, because you know with exponentials the power doesn't change when you differentiate them. Or should it be an ax plus b? Or should it be an ax squared plus bx plus c? Or should it be an a e to the x? Or should it be an ax plus b e to the 2x? Or should it be an ax squared plus bx plus c e to the kx? Oh my god. Okay, what form should we try for our f of x? And you're just guessing, so don't worry about it. It doesn't matter if you get it right or wrong, but you're just guessing. You can't know in advance. It's just using your intuition. To Shane.
Would it be like a e to the kx?
A e to the kx. What happens if you differentiate a e to the kx? Still to Shane.
You get a k e to the kx.
Can you have an x at the front here? A is just a number, remember, and k is just a number. Can you? Has that managed to get you an x at the front there?
No, so
So that's not going to work. And also, you know the k here, did the power change at all when you differentiate it?
no.
So the power didn't change. So maybe you don't need to use a k, because you know that if you leave it as e to the x, it will stay as e to the x. And then when you add these two together, you'll just get an e to the x term. So the k doesn't need to be there. But also we've got a problem because the x isn't there. Try again. Shruti.
Maybe ax e to the x.
Ax e to the x. Okay, good. Okay, so that's going to be our f of x. What would be our f dashed of x in that case? F dashed of x. Let me just rub that out.
The same thing.
Same problem, did you say?
The same thing. No.
No. You have to use the product rule. Come on, Shruti.
Oh,
Differentiate the
so
first one.
that's just ax half ax squared
Differentiate the ax.
half a.
Differentiate. Integrate. Just differentiate.
Oh, sorry. A.
And then multiply it by the second one. E to the x. Plus.
E to the
Differentiate
x.
the e to the x.
E to the x.
Multiply it by the first one plus
Ax,
ax e to the x. So what you end up with is you end up with 2ax e to the x plus another a e to the x. Now what's gone wrong, if anything? If anything's gone wrong, what's gone wrong? Should these said if we start with this, we might be able to end up with this as our answer. And we started with it. Has anything gone wrong or has it worked? And if anything has gone wrong, what is wrong? Joe?
The a e to the x isn't part of the answer.
Yeah, we can't have that in there, and we don't want it in there. And the only way to get rid of it would be to make a naught, but that would make everything naught, and it wouldn't work. So we would be completely flummoxed in that case. So I think Shruti's guess wasn't quite right, and the reason it wasn't right was she couldn't have known it beforehand. But if this is your guess, it's going to give you some more x e to the x's, but it's also just going to give you some e to the x's on their own as well, and that's not great. We don't want them. We don't want any e to the x's on their own. Okay, so we're going to have to rethink. So let's have another go.
E to the x times a plus ax plus b.
Yeah, okay, well done. Ax plus b times e to the x. So Shruti said, why don't we choose this as our f of x? F of x. When we differentiate that, what does that give us? Devansh. Differentiate the first one, multiply it by the second one, plus differentiate the second one, multiply it by the first one.
So you get a e to the x.
A e to the x.
Plus e to the x times ax plus b.
Yep, splendid. And we need to simplify this. So you've got an ax plus b e to the x, you've got another ax plus b e to the x, and you've got an a e to the x. So let's factorize the e to the x out from there. And then what does that give us in the brackets?
You get a plus ax plus b.
You've got, so we're factorizing e to the x out. So that would leave us with an ax plus b here, and it would leave us an a here, and it would leave us with an ax plus b there.
Yeah.
Go on. Factorizing e to the x out of all of this.
So you get 2ax plus 2b plus a.
Okay, lovely. Okay, so now what we wanted was we wanted 2x plus 0 times e to the x. So that tells us that a is going to have to be 1. A is going to have to be 1 because that has got to match that. And then this has got to match that. But we already know that a is 1. So a is 1. And so 2b plus 1 is going to have to be 0. And so b is going to have to be minus a half. So that tells us that b is going to have to be minus a half. So the answer is x minus a half e to the x is the correct function to use if we want the function plus its derivative to equal 2x e to the x. Okay, so let's move on. And let's differentiate. So this is just using the product rule to differentiate. So just checking you know how to use the product rule to differentiate. So differentiate the first one, 1, multiply it by the second one, y, plus differentiate the second one, dy by dx, multiply it by the first one, x. So y plus x dy by dx. You see this a lot, differential of x, y. You see it a lot, and it gives you y plus x dy by dx every time. Next one, product rule. Joe.
Sin x plus y cos x.
So differentiate the first one.
1.
When you're differentiating
I mean,
y,
wait.
you get
yeah.
1 dy.
D by dx. Dy by dx.
1 dy by dx. Because remember, you're differentiating y, but you're differentiating with respect to x. So
Yeah.
that gives you 1 dy by dx. When you differentiate y squared, when you differentiate it with respect to x, you get 2y dy by dx. You have to multiply it by a dy by dx at the end. So that gives you, differentiate the first one's dy by dx, multiply it by the second one. So dy by dx times sine x plus, carry on, Jay.
Cos x y, or y cos x.
X. Splendid, good. Next one, to Shane.
2e to the 2x multiplied by y squared plus 2y e to the 2x.
Did you
And then
differentiate?
e to dy by dx.
Yeah, perfect. Perfect. Okay. Next one. So it says here, u is a variable, not a constant. So when you differentiate u, you're going to get du by dx because it's not a constant, it's a variable. Next one.
So it'd just be 1. What? Just be x.
No. Differentiate the first one.
So differentiate with the first one would be du by dx.
Du by dx. Multiply it by the second one.
Okay. So du by dx times x, and then it would be differentiate of the second one. So it'd be 1 times u. So u.
Okay,
and then you
lovely.
just add it.
Oh, hold on. I didn't spot that. It says d2 by dx squared of ux. So they need us to differentiate it twice. We've only differentiated it once. So, okay, well, never mind. We're just going to have to differentiate it again. D by dx of that. So we need to differentiate this again. So let me just rewrite that a bit neater. So that says x du by dx plus u. So we're differentiating again, Devansh?
Can I write it down, sir?
Yeah.
So you use the product rule for the first term.
Yes, you do.
So you get du over dx.
Yeah.
Then you get x d squared u over dx squared.
Perfect, good.
Plus
you get x d2u by dx squared plus du by dx. Carry on.
Plus du over dx.
Plus another du by dx. So you could just combine those together and call it x du by dx plus 2 x d2u by dx squared plus 2 du by dx. Okay. Okay, now we need to do this one. Okay. So this time p is a constant, not a variable. P is a constant, not a variable. So how do I differentiate this? It's the product rule again. Shruti. Microphone.
You differentiate the first one, which is minus p e to p minus px, and then times by y, and then dy over dx.
Yeah.
And times by e to the power.
Okay, so that's the first differential. You've done that splendidly. But
and then product rule.
It says differentiate it twice.
Yeah.
We've still got one more differential to do. You're happy to keep going?
Okay.
Wait, sir, is that a dp by dx on the first time, or is that?
So p is a constant. So
Yeah.
you don't have. You never get dp by dx.
Yeah.
You never get dp by dx.
Sorry.
So you're going to get minus p e to the minus px, which is differential of the first one, times y plus e to the minus px times dy by dx. Okay, off you go, Shruti. You need to use the product rule again here.
So p squared e to the minus px y plus dy over dx minus p e to the minus px.
e to the minus px
And
y by dx.
then minus p e to the minus px times dy by dx.
Yeah.
Times d2y by dx squared times e to the minus px.
Splendid. Do you want to factorize e to the minus px out from all of that? So
Yes.
e to the minus px.
So that's p squared y.
So p squared y.
Times
These are the
p.
same term, Shruti. That one there and that one there are the same.
Oh yeah.
Minus p
Minus
minus
2.
p.
Minus 2. dy by dx. And it's p squared or wait. Just dy by dx.
d2y.
Oh yeah,
So that's
d2.
the last term there.
Yeah.
That gives you e to the minus px d2y by dx squared minus 2p e to the minus px dy by dx plus p squared y. Incidentally, these numbers are quite interesting. There's a 1 at the front here, there's a minus 2p here, and there's a p squared here. And if you had an equation like this, x squared minus 2p, let's not use x, let's use u squared minus 2pu plus p squared, you would say to yourself, oh, that factorizes very nicely. That's just going to be u minus p all squared. So there's something interesting about this, but we won't know what for a little while yet. We need to get to that. Okay, so that's just the product rule, revising the product rule. And now I want to go back to differential equations. So we learned how to solve differential equations when they're separable. So in A-level maths, the only type of differential equation we learn to solve is one which is separable. Separable means you can get all the y's onto one side and you can get all the x's onto the other side. And the way you do that is, first of all, by isolating the dy by dx term. All of this is the dy by dx term. So we need to isolate that first. So that gives us 2y brackets x plus 1 dy by dx equals 4 plus y squared. Okay, so we've isolated the dy by dx term. That's great. Now, using only multiplication and division, once you've isolated the dy by dx term, we're only allowed to use multiplication and division, and we want all the y's on the left-hand side, where the dy by dx is. And we want all the x's on the other side. And you're only allowed to use multiplication and division. So when you start speaking, either start with the word divide by blah, 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 or start with the word multiplied by. Don't start with anything else. Don't start with when is Diwali going to arrive next year or something like that. Don't just start with multiply or divide. So, and it's not always possible. So the answer is it separable? Well, it's separable if you can get all the y's on the left-hand side and all the x's on the opposite side using only multiplication and division. What would you like to do first, Devansh?
So we're differentiating it. So
no, you
use
failed. You failed, Devansh. The rule was you're only allowed to start with the word multiply or divide. They're the only two things. Your sentence has to start with either multiply or divide. You cannot say anything else to me. You cannot say, so my throat is hurting and I think I might have meningitis and I'm dying. You can't say that. You have to start with the word multiply by something or divide by something. Tashane.
Divide by x plus 1.
Divide by x plus 1, divide by x plus 1, divide by x plus 1. So that gives me 2y dy by dx equals 4 plus y squared. Although you said divided by x plus 1, I'm still only going to write it at the end because the y's and the x's don't love each other anymore when we're separating the variables. They're separated.
Dr. Shah?
Yeah.
wouldn't it make sense to put the divide by 2y, so the y's are on the same side?
No, well, the rule is the y's have to be on the same side as the dy by dx. So yeah, it kind of does.
Oh, okay.
The rule is the y's have to be on the same side as the dy by dx, and the x's have to be on the opposite side. So, I mean, you can do it the other way around, but then you end up having to recip it, and it just gets messy. So we won't do it that way. We'll always bring the y's on the dy by dx side. Carry on, Shane.
Divide by 4 plus y squared and then multiply by dx.
Divide by 4 plus y squared, and so that's going to give me 2y over 4 plus y squared dy equals 1 over x plus 1 dx. And have you successfully got all the y's on the left hand side and all the x's on the opposite side using only multiplication and division, to Shane?
Yes.
Then it's a separable, then you've separated the variables, then it's a separable, a first order separable differential equation, which means we can solve it. We just put an integral in front of both sides, and we just need to integrate this. We know our guess for this would be ln of 4 plus y squared. And actually ln of 4 plus y squared does give you 2y over 4 plus y squared, so that's perfect. Equals ln of x plus 1. I need a modulus here. Ln of x plus 1. We need a constant, and we always like putting our constant inside the log because it's better there. So I'll put an a inside here. And then now I'm just going to do e to the power of this side and e to the power of this side. And so that's going to give me 4 plus y squared equals a brackets x plus 1. And then y squared equals a brackets x plus 1 minus 4. I'm not going to try and make y the subject because it's going to look ugly if I do that. You have a plus or minus square root. We won't like that very much. So that's a first order separable differential equation. If we wanted to carry on any further, that means we'd need to find the a. To find the a, they'd have to give us some numbers to put in, because when you're solving a differential equation, you're effectively integrating. And when you're integrating, you get an unknown constant. And to get rid of that unknown constant, they need to give you some numbers to put in. They haven't, so we will just terminate it there. Next one. Again, it's recapping on stuff we did last year. So it's recapping on first order separable differential equations. So that means your rules are, you need to isolate the dy by dx term. The dy by dx term is all of that. Everything next to the dy by dx up to the next equal sign or the plus sign or the minus sign or something like that. Yeah. So that's the dy by dx term. You need to isolate it. Well, it's already isolated, so there's nothing to do in terms of isolating the dy by dx term. The next step is using only multiplication and division, collect all the y's on the left hand side and all the x's on the opposite side. Your sentence must start with multiply by blah, 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 or divide by blah, blah, blah. I don't care if a mad axeman breaks in and is killing you, your sentence still has to start with multiply by or divide by. Devansh.
Divide by tan x.
Divide by tan x. So divide by tan x. Divide by tan x.
And divide by 2y squared.
Divide by, you don't need to take the 2 if you don't want to. You can just take the y squared. Divide by y squared. And you can take the 2. You can take the 2. Oh gosh, what happened there? Okay, divide by y squared. You can take the 2 as well if you want. I'm not going to bother taking the 2 now because it went wrong when I tried to. Equals 2 sec squared x over tan x. Have you successfully got all the y's on the dy by dx side and all the x's on the other side using only multiplication and division?
Yep.
So that's your variables separated. So now we just integrate each side and take the dx to the top here. Integral of 1 over y squared, that's integral of y to the minus 2 effectively. Integral of 1 over y squared, Joe?
Would it be ln one over
add 1 to the power, divide by the new power. Simple polynomial integration, add 1 to the power, divide by new power.
it would be y to the minus 1, so then it would be 1 over minus 1, so minus y.
And integral of 2 sec squared x over tan x. What's your guess going to be?
Would my guess be
Doesn't that
tan-
learn f of x?
tan x?
Yeah. So Shane noticed that this was this thing here, but it actually wasn't, because when I said this here, I mean exactly that. I mean not some equations, but actually f dash x, those actual words, f dash x over fx. If we see integral of f dash x over f of x using actually f dash x and fx, not using sec squared x and tan x, but using actually f dash x, then you have to shout ln of f of x in that situation. So Shane, you were right, it was that situation, but I need to be more precise. What I meant is when it is actually f dash x over f of x. So carry on, Joe.
Would it be 2 ln tan x?
2 ln tan of x. Where do you want your constant?
Can make it ln k.
Okay.
Tan x.
Okay. And then I don't know if I'm going to do much about that. I'm going to rewrite that as 1 over y equals minus 2 ln k modulus of tan of x. And then if you want, you could recip both sides, but I think I'll just leave it like that. Okay, so those are first order separable differential equations, and that's what we learned last year to do. And so now what we want to move on is we want to start looking at other types of differential equations. This is the most powerful topic we're going to learn in further maths. This is the most useful topic we're going to learn. Okay, so differential equations. So types of differential equations and how to identify them. So an nth order differential equation will have dny by dxn. In other words, a second order one will have d2y by dx squared in it, but it won't have d3y by dx cubed in it. Whereas a third order will have that, have d3y by dx cubed in it. A first order will only have dy by dx in it. It won't have d2y by dx squared in it. As soon as it's got d2y by dx squared in it, it becomes second order. If it's linear, then the y term will only contain y. It won't contain y squared. So all of these can contain x's in front of them. So that can have some function of x in front of it. That can have some function of x in front of it. That can have some function of x in front of it. That can have, and that can be a function of x. There can be functions of x all over the place. Nobody cares about those. But the y term will just be y. It won't be a y squared. It won't be a y cubed. It won't be a 1 over y. It won't be a ln y. It will just be y. That's what makes it linear. That is what makes it linear. So a second order linear one would be, it would have a d2y by dx squared, it would have a dy by dx in it. These can both have functions of x in front of them. And then it will have a y, because it's linear, it only has a y, it doesn't have a y squared or a y cubed or a 1 over y or anything like that. Again, that can have some function of x in front of it, and it can have some function of x at the end of it. So second order linear, it's second order because it's got d2y by dx squared in front of it. So that's what makes it second order. And it's linear because it's got the y. It hasn't got the y squared or the y cubed or anything like that. You know, I haven't put some equation in front of the d2y by dx squared. That's not because there can't be one there. It's because there was one there and I divided through by that equation. So if there was an x squared at the front of there, maybe I divided everything through by x squared, which got rid of the number in front of the d2y by dx squared. So it's just me saying, yeah, but I don't like to have, I'm just dividing through to get rid of that. Okay, so now we've got first order. So first order means you can't have d2y by dx squared in it. You can only have dy by dx in it. Remember, this could have a function of x in front of it. This could have a function of x in front of it, and that could be a function of x. But now it says linear. Linear means that that can only be a y. And then it says with constant coefficients. Now constant coefficients means that that can't be some equation with x in it. And that can't be some, so constant coefficients, these are called the coefficients, these here. And if the coefficients have got like an x squared or an x cube in them, then they're variable coefficients. But these are going to just be constant coefficients. So that's going to be an a, that could be a b if you wanted in front of there. But again, I would probably divide by the b and then replace that b over a with a new letter or something like that. So I never end up with a number in front of my dy by dx just because I can easily divide through by it and get rid of it. So this is first order linear with constant coefficients. And we're going to need to know these names because the names are going to tell us how we're going to approach the equations. So during A-level maths, we only did first order differential equations with separable variables. But now we're going to start opening up the whole world of differential equations, and it's going to get a lot more interesting. It's going to get a lot more exciting. Okay, so the first type of differential equation that we're going to start studying is first order exact equations. And I'll tell you what I mean by an exact equation. Let's start off with this and let's differentiate this. So this is not a differential equation. This is just me asking you to differentiate something. Over here is a differential equation because it's got a dy by dx in it. So this is just a bit of algebra, some equation, some function, some algebraic thing, and I just want you to differentiate it. And you're going to have to use the product rule, obviously. So when you differentiate that, it gives you Joe. Joe?
It would be y squared plus
Lovely.
2y dy by dx
Yep.
times x.
2xy dy by dx. Carry on.
And it would be e to the 2x.
Perfect. Good. You differentiated this using the product rule and you got that. Okay. And then the right-hand side is, I'm not interested in the right-hand side. It's boring. I don't care about it. I'm interested in that left-hand side and that product rule that you used. Now, I'm going to give you a different question. So now we want to try and undifferentiate this equation. Undifferentiate. I called it undifferentiate it. Of course, what I mean is integrate. But I'm just reminding you that integration is the opposite of differentiation. So if integration is the opposite of differentiation, what you're trying to do is think about what someone might have differentiated to get this. What might they have differentiated to get that? And then you could undo it by just telling me what that answer was, and then you'd have effectively integrated it. So I want you to integrate this, asking that to Shruti.
Xy squared.
Lovely. How did you know that?
Because we just differentiated it and got that answer there.
It's identical to that. So we know that that comes from differentiating this. So we know if you differentiate that, it gives you that. And so we know that if you want to integrate that, it's going to give you xy squared equals, and if you're going to integrate the left-hand side, you also have to integrate the right-hand side, Tree.
So ln x squared plus 1, and then divide by x.
What's the difference of ln x squared plus 1?
2x.
Okay, and what do you need to get rid of?
You need to get rid of the 2, so half.
Okay, and we need a constant in there somewhere. Oh, I didn't leave room to write it inside the list. I'm just going to write a plus. Yeah, I didn't leave room though, so I'm stuck. Room there. So, okay. So this is a differential equation, and we actually solved it just now. So that is a differential equation, and we've solved it just now. We've solved the differential equation. Okay, what about this one here? It looks so similar to the last one. Can we do the same thing? Can we call it xy squared equals, and then integrate this side, which we know is going to give us half ln x squared plus 1. Can we do the same thing? Is it going to be the same? To Shane?
No.
No, because we know that xy squared gives us 2xy dy by dx plus y squared, and that's it. Okay, well, can't I just halve it then? Can't I just halve it? Will that fix it?
No, because it has to be a constant for you to do that.
Yeah, okay, so that won't work either. Okay, so what we've learned is even a slight change here, a tiny little change here, getting rid of that 2, all of a sudden means that it's no longer exact, and we are now stumbling to try and figure it out. But we'll figure it out. We'll figure out how to do questions like that in a second. Okay, so what we're going to do, first of all, is we're going to get the terms in order. So we want the dy by dx first term, then we want the y term next, and that will have some x's in front of it. It doesn't have to, but it can have some x's in front of it. And then on the right-hand side will be the only x's term. So it's got only x's in it. Okay, so we're going to get x squared dy by dx plus 2xy equals 1. Okay, now what we're going to do is ask ourselves, could this be an exact differential equation? Could it be like this one here, where we can easily integrate it? And the way we're going to do that is we're going to look at these factors. So we're going to look at these factors, we're going to look at this factor and this factor, and we're going to look at this factor and this factor. And you notice I'm highlighting the x bits in green and the y bits in blue, and the dy by dx bit counts as a y bit, and so it goes in blue. What I'm looking to see is, if you differentiate this, does it give you that? If you differentiate this, does it give you that? Yeah?
Yep.
Okay. And then if you differentiate this, does it give you that? Still here.
Yeah.
Yep. Differentiate y with respect to x, you get dy by dx. So then if they match up, yeah. If they match up, that means that somebody used the product rule. And what did they start with, Shruti?
X squared y.
X squared y. Yeah, the two ones at the start of each arrow. The two ones at the start of each arrow, not the ones at the end of each arrow. So x squared y. What you've now done is you've integrated that. By undoing the product rule, you've integrated it. What do you need to do on the right-hand side?
To integrate as well. So x.
There we go. So we've solved that differential equation. And we've solved that differential equation because we were able to identify that somebody had used the product rule to differentiate it. And the way we identified it is with these nice little arrows. Next one. Okay, so first thing we want is our dy by dx term on its own. Then we want our so we want our dy by dx term first. Then we want our y term, that can have x's in front of it if it wants to, and then we want our only x's term on the right. So it's already nicely arranged. We don't need to worry about the arrangement of this one, so that's fine. Okay, so now what we're
Dr. Shah, didn't you say that we can't have anything in front of the dy by dx?
No, I said I tend to get rid of it. If there is something in front of the dy by dx, I tend to get rid of it, but I'm not going to at the moment. But later on when I write them, you'll see I do tend to get rid of it a lot. So it's not that you can't have it, it's that the reason I didn't bother writing it in there is because it would be possible to get rid of it. So the reason I didn't write it in here is because by not writing it in here, I'm not wrong. Because if there was an x squared in front of there, I could divide through by x squared and it would go. So it's not wrong to not write it in there. Okay. So, right, so let's try and match them up. So we've got the x bit here, and there isn't really an x bit here. Let's just call the 1 the x bit then, and the y bit here is the y squared, and the y bit here is the y dy by dx. Does it match up? Does it match up? Does the y squared differentiate to give me y dy by dx? And does the 2x differentiate to give me 1? It's not working, is it, here? Hold on a second. What does y squared differentiate to give you here?
2y dy by dx.
So what I'm going to do is, you know this 2 here? I'm just going to pick up that 2. Okay, well, let me pick up the 2. Okay, what I'm going to do is I'm going to hide the 2. And the way I can't rub it out, so I'm hiding it by just...
Can't you just times it by a half?
I don't need to times it by a half, but what I'm trying to do is I'm trying to move the 2. Okay, you know what? I'm just going to write it again. So I'm going to write it as x2y dy by dx plus 1y squared equals e to the x. All I've done is taken that 2 and just moved it in the middle here. Moved it into there, which is still the same. It looks a bit weird, but it's still the same. And now that's my x and that's my x. And that's my y and that's my y. So does it match now, Het?
Yeah.
And does this one also match now, Het?
Yeah.
And so somebody must have used the product rule and they differentiated it and they got this. What would they have started off with, Het?
So x 2y dy by dx.
No.
I mean 1y squared.
x times y squared, the beginning of each of the arrows, the front of each of the arrows. That arrow goes there, but its start is here, the y squared. And that arrow goes there and its start is x. So if somebody started off with xy squared and they used the product rule, they would get 2xy dy by dx plus y squared. And we've just undone it. So effectively we've integrated. Let's just write integrate there. And that means we need to integrate this e to the x. What happens when you integrate e to the x here?
Stays e to the x.
And then we just need a plus c. And so there's our answer. So we've solved that differential equation and it was easy to do. Okay, so we need the dy by dx term first. Then we need the y term. Okay, that's over here. It shouldn't be over here. It should be on the left. And then we need the only x's term. That should be on the end after the equal sign. So can you just rearrange this for me, Devansh?
X squared cos y dy over dx plus 2x sine y equals 1 over x.
And then this is going to be my x bit, and this is going to be my y bit. Can you tell me, does it all match up, Devansh?
Yeah, it does.
And so if I ask you to integrate the left-hand side, what would you say the answer was?
X squared sine y.
X squared sine y. Splendid. And you need to integrate the right-hand side as well.
Ln x.
Where do you want your constant?
Right hand side.
Inside the ln.
Oh, okay, yeah.
Okay, and so that's it. That's that question finished. Okay, next one. We need to get the terms in the right order first. Joe.
Would you have to divide by? Oh no.
No, just moving.
You can add. So you can add e to the y.
X e to the y dy by dx plus e to the y equals 2. Now I'm going to highlight the y bits. There's a y bit and there's a y bit, and then I'm going to highlight the x bits. Oh, there isn't really an x bit, so what I'll just do is I'll just put a 1 there. That will do. No one's going to care if I just put a 1 in there. Does it all match up, Joe?
Yes.
Yeah, when you differentiate e to the y, you get e to the y dy by dx. When you differentiate x, you get 1. And so what's my answer still, Joanna?
X e to the y.
And on the other side?
It would be 0.
Integrating it?
Oh, integrate to 2x.
And so e to the y equals 2 plus c over x. And then y equals ln 2 plus c over x. I don't know if it's necessary to do the ln there, but I've done it anyway. Next one, to Shane.
Would you have to factorize the y on the right?
Yeah. Oh, I see what you mean. You've got 2 terms with y's in them, and you only want to have 1 term with y in it. You don't want to have 2 terms with y in it. So yes, you're right. I mean, ideally, what I'd want is I'd want sort of a dy by dx term, and then I'd want a y term, which can have some x's in front of it, and then I'd want some x terms here. So you could factorize the y out. It's going to make this term quite complicated. So the alternative to factorizing the y out would be to divide by y. If you divide by y, that would get rid of the y from this. It wouldn't get rid of the y from that. You'd still have a ln y here, so you wouldn't get rid of all the y's from this one. So then you could get it like this, and maybe it would be easier than having that big clump together term. You can do that as well, but it will be more complicated, and you might struggle to get to an answer from there. Carry on.
So x squared over y dy by dx is equal to 3.
Are you going to move the terms as well? You might as well do it on the same line.
Okay, so plus 2x ln y equals 3 cos x.
Okay, so I'm trying to match up the things again. What I'm going to do is I'm going to slide that x squared off the top, because you know, the x's and the y's kind of are sort of a bit being separate from each other as well. So I'll leave that as a 1 over y, and I'll put the x squared at the side there. So my x's are like the x squared and the 2x, and then my y's are like the ln y and the 1 over y dy by x. Does it all work, Tashane?
Yes.
Yeah. And so if you were to give me the answer for this differential equation, it would be
x squared ln y is equal to, and then you integrate the right hand side.
Yeah.
So that's 3 sin x.
And then we need a plus c. We could put an a inside the ln there. I know we normally put it on the right hand side, but the ln is always a tempting place to put the constant, isn't it? I mean, that's where we favor putting our constant in there. And so that gives us ln a y equals 3 over x squared sine x. You could do e to the power of both sides. So a y equals e to the power 3 over x squared sine x. I'll put the sine x on the top there. And then y equals c e to the 3 sine x over x squared is my final answer. Okay. Let's skip that one. We've done quite a few of these. Okay, last one. Okay, so we want our dy by dx term, then we want our y term, and then any x only terms have got to be on the other side.
Could you repeat what you just said again?
You want your dy by dx term. I mean, it's the same as we've done on all the others. We want the dy by dx term first, then we want the y term, then we want any x only terms on the right hand side.
So be y dy by dx plus y squared is equal to 3x over x.
I don't know why you divided by x. We're only moving the terms at the moment, so I'm not sure why you divided by x. It wasn't necessary to divide by x. All we were doing was moving this y squared here, because the layout has to be dy by dx term, then y term, which can have x's in front of it, and then only x's term here. So that's the layout that we're after. Okay, let's try and match it up. X1 and y squared dy by dx. So y squared differentiates to give you y dy by dx, and x differentiates to give you 1. That's all perfect. And so that gives us our answer as being
how is y squared y dy by dx?
Isn't it? Oh, okay. All right, I'll fix it. Don't worry, I'll fix it. I can fix that. I'll put a 2 in front of there. There. Is that better? Are you happy now?
No, because you changed the...
Okay, fine. I'll put a half in front of here. Then I fix it. If you multiply by 2 and you multiply by a half, then you fixed it. So now the y's match up lovely. And I haven't changed anything.
But then the x don't match up. Oh yeah.
Oh my God, you're just finding problems now. Yeah, you're right. The x's don't match up anymore. Okay. You're right. Oh crap. Okay, hold on. We can still fix this. How about we multiply through the whole equation by x? So we multiplied through the whole equation by x. So the equation now becomes a half x squared 2y dy by dx plus, I'm multiplying that by x, xy squared equals 3x squared. Is that still effectively the same equation? All I've done is multiplied through by x. I know I've put a half and a 2 here, but they don't make any difference. They just cancel out anyway, so that doesn't make any difference at all. It's still the same equation, isn't it, Harrow?
Yeah.
Okay. Now, do the x's match up?
Yeah, the X is match up.
And do the y's match up?
Yeah.
So are you happy now? You're going to stop complaining about how the things don't match up and how you have to do it properly, and it's his maths, you know, you have to do things by the book. It's not like history where you can just make up any old nonsense you like and then say that that's history. Okay, so let's integrate this then. What do we get, Het?
So if you integrate half x squared, so it'd be half x squared and y squared.
And integrate the other side.
So it'd be 3 over 2x cubed.
Add 1 to the power, divide by the new power.
Oh, 3x cubed over 3, so x cubed.
And plus c. And then I'm going to multiply through everything by 2. And then I'm going to divide everything through by x squared. So y squared equals 2x plus c over x squared. And I'll leave it like that. I won't go anymore. Now, the problem is here, I said, why don't we multiply it through by x? And you should be feeling a little bit jittery now. Well, what's he going to expect us to do next? Multiply it through by ln x? Multiply it through by x e to x? How am I going to know what he wants me to multiply it through by? And so that's what we're going to learn now. The thing that you multiply it through by is called an integrating factor. So in the last one, I had to multiply it through by x. So that's my integrating factor, was x. Okay, so what we're going to do is we're going to do first order differential equations using an integrating factor. So the last one was first order exact, but now we're going to do first order using an integrating factor. And this is slightly complicated, but it becomes really simple. So it starts off really complicated and you think, what's going on, what's going on, what's going on? And then it becomes really easy. Okay, so just reminding you that a first order linear differential equation would have a dy by dx, and then it would have a y here, but no y squareds or y cubed. You could have a 2x at the front there. You could have an x squared at the front there. It doesn't matter. And then you just have some x equation here. Same here, some x equation here. You've got a y here. You've got a ln x in front of there. That's perfectly okay. This is non-linear because in this case, you haven't only got a y term, you've got a 1 over y term as well here. And so either you join those two terms together or you multiply through by y, in which case it stops being linear. You have a y squared somewhere. It's no longer a linear one. So, okay. So first order integrating factor. So this is an example of a question that we want to try and solve by using an integrating factor. And if we weren't going to use an integrating factor, we would try and ask ourselves, is this an exact differential equation? So what we would do is we would write 4y tan x dy by dx plus 4y squared equals sine 2x. And then we would try and match them up. We would try and match up the tan x with maybe the 4, and we would try and match up the y squared with maybe the 4y dy by dx. And of course, the y squared is going to give you 2y dy by dx, so we can match that up, no problems at all. What we can do is we can match that with all of this. I need to make that a 2, so I'm just going to change that to a 2. I know Het's going to get upset about it. He's going to get all het up over it. Okay, all right, it wasn't funny then. So I will just put another 2 next to the tan x to make that one the same. But then what happens is my x's don't match up. They just don't match up. The 2 tan x does not differentiate to give me 4, and it doesn't seem obvious what we can do to fix it. Not like the last one, you can't just multiply through by x. It's going to be a lot more complicated. Okay, so what we want to do is we want to find a way of always knowing how to fix that problem. Okay, so a systematic approach would work like this. So first of all, arrange the terms. We did that already. We know you have to do that. We're not foolish. We know that you have to arrange the terms. So it's 4y tan x dy by dx plus 4y squared equals sine 2x. So we've got our dy by dx term, then we've got our y term, and then x onlys are on the other side. Okay. Arrange terms. We've been doing that on all the questions anyway. Identify the derivative of the y factor in the second. Okay, but that's what I was doing anyway. I did that earlier on. When I did that, I looked for, I said, look, the differential of y squared, I said the differential of y squared will be 2y dy by dx. So what I'm going to do is, so I'm going to move that y to there, next to the dy by dx. And that 4, I'm actually going to get rid of the 4. So I'm going to get rid of that 4, but I'm going to replace it with a 2 here and a 2 there, which is what I did before. It's nothing different from what I did before. And then I'm going to highlight the 2y dy by dx. Okay, so I have matched up the y squared with a 2y dy by dx. So I've matched that up, and that's worked perfectly, but that's what happened before. What didn't happen before was the 2 tan x doesn't differentiate to give me 4. I know that's the problem. Okay, so far I've not done anything new. Do the same thing as we've done so far. Okay, so that's the same situation again. Now it says if there are any x's in front of the dy by dx term, then divide through to get rid of that. And remember, I did say to you that often I will get rid of anything at the front here. I'll just divide through by 2 tan x. So I'm going to divide through by 2 tan x, and I'm going to divide through by 2 tan x. So I just want to get rid of that 2 tan x. Just want to get rid of that. Okay. Oh, I can simplify that. The 4 and the 2 will cancel down. That will give me a 2 on the top there, and that 2 will go. And then the sine 2x. What if I expand the sine 2x? It could be 2 sine x cos x, and then the tan x, I could change that for sine x over cos x, in which case the 2's would cancel out, the 2's would cancel out, the sine x's would cancel out, and then you get cos x over 1 over cos x, which gives you cos squared x, which gives you cos squared. That's just tidying up. I know you know how to tidy up a little bit of trig like that. Okay, so that's what we've ended up with. We've ended up with 2y dy by dx. Oh, what happened here? We had 2 over tan x, and it's changed to 2 cot x. Is that okay, Tashane? We had 2 over tan x here, and it's changed to cot x. It's the same thing. It's the same thing. Nobody cares about that. Okay. Now, right. So now this is the clever bit. This is the interesting bit. This is the complicated bit, but it's not that complicated once you know, because it's a procedure. So explaining it is complicated, but doing the procedure is easy. We'll do the same procedure every time and it will become easy. Okay. Now imagine that there was something that we could multiply through this whole differential equation by. So all we've done is we've matched up the y's like we normally do, and then the x's didn't match up. So we said, all right, let's get rid of the crap at the front. Let's get rid of the crap at the front. So we got rid of the crap at the front, and now we still need to figure out how to make the x's match up. So imagine you could multiply through by something called fx, some integrating factor called fx. Let's imagine you could multiply the whole equation through by fx. So you multiply the equation through by fx. You multiply the equation through by fx. You multiply the equation through by fx. Let's imagine you could multiply the whole equation through by fx, and that fixed the problem. So you multiplied the whole equation through by fx. You multiplied the whole equation through by fx. You multiplied the whole equation through by fx. And imagine that that fixed the problem. Okay? So that's what happened in that last example that we actually did, where I said, let's multiply through by x, and it fixed the problem. So we're going to imagine you could multiply through by fx, which is what I've done here, and that fixes the problem. But obviously, that's lovely to imagine that, but we've got to know what we mean by multiplying through. What is fx going to be? What is fx going to be? What is the thing that we need to multiply through by? In that previous example, it was a very simple example, and the thing we had to multiply through by was x. But this is a much more complicated example, and we can't at first glance see what we're going to multiply through. We can't guess it. We're going to have a way of figuring it out. So what is that fx going to be? Well, here's the clever bit. We know that this has to differentiate to give us this. Yeah? We know that whatever this is has to differentiate to give us that, don't we? Because that's the rule. That's how you match it up. So in other words, this thing here has to be f dashed x. Whatever this whole thing turns out to be, it has to be f dashed x. It has to, because otherwise it won't match. That, when you differentiate fx, you get f dashed x. So that whole thing inside there has to be f dashed x. So, this thing here, the 2fx cot x has to be f dashed x. I can see you're getting a bit excited and jittery there, Shruti. So let me just get to it. So f dashed x, when you differentiate it, it's got to give you this. In other words, f dashed x has got to equal 2fx cot x. And that's obvious. That's all I'm saying. I'm saying when you differentiate that, you got to get that, which means that's got to be f dashed x. And all I've said is f dashed x has got to be 2x. Now I'm going to divide through by fx. Now I'm going to divide through by fx. And then
learn fx.
I hadn't said it yet, but you'd already preempted it. You knew that what I'm going to do is I'm going to integrate both sides. And the reason you knew I was going to integrate both sides, because that would be the magic thing that we were looking for earlier on. We knew that we were looking for integral of f dashed x over f of x, and we know that that gives us ln of f of x. So ln of f of x, I'm not going to bother with the modulus because I'm going to get rid of the ln in a second, equals, I've forgotten what the integral of cot x is.
Ln tan.
It's a shame you told us it earlier on.
Ln sec of x.
Ln sine of x.
Sorry, sine x.
Ln sine of x. Okay. Now, remember, we were trying to figure out what fx is. So we need to make fx a subject to this. What would you suggest we do next, Joanna?
Please, can you repeat that?
We need to figure out what fx is. That's what we wanted all along. That's all we were after the whole time. We wanted to know what fx is. How can you get fx?
You can do e to the power.
Before you do e to the power, what would you do first?
Divide by 2. I'm not sure. I thought you want f of x, right?
I do want f of x, and you're right in saying I have to do e to the power of both sides, but there's something that obviously should be done first.
Put it to the power.
Yeah, because then both of them start with a ln at the front then both of them start with a ln at the front, and so if you do e to the power of both sides, e to the power, e to the power, then it gives you fx is sine squared x. We figured it out. It was sine squared x. The thing that you have to multiply is sine squared x. We figured it out. It was sine squared x. Now, we're not going to go back to that example. We haven't finished that example. All we figured out is what you'd have to multiply it by in order to make it work. But we're not going to go back to that example. We're going to carry on and do the next example. So this is me saying the same thing. You know, the differential of that has got to be that. So that's got to be f dashed x there. And so f dashed x has got to be this. And so f dashed x over f. It's just me doing the same thing in more theoretical terms, but you don't really care about that. And then, so that gives you that. And then, so fx is going to be e to the integral of that. What we did, if you look back at what we did here, is we looked at this thing here, and what we did was forget the fx. The rest of it, the 2 cot x, what we did was we integrated the 2 cot x. And then after we integrated the 2 cot x, we did e to the power of that. So we integrated the 2 cot x, and then we did e to the power of it, and that's what gave us our answer. So this is what this is telling you. What you need to do is you need to integrate the function that's next to the fx, and then you need to do e to the power of that integral, and then that will give it to you. We'll do a couple of examples, and that will make it completely clear. Okay, so we'll do some examples. So, right, what's the technique? And we're actually going to change the technique. So we're going to do the technique fully first, but actually that's not how we do it. So first of all, get the terms in order, and then do the y, match up the y thing. Okay, so let's get the terms in order first. So we're going to get 2xy dy by dx. 2x, oh, I forgot the 2. 2xy dy by dx plus 3y squared equals e to the x cubed. Okay, so we're going to match up the y squared. Well, it's going to match with a 2y dy by dx, isn't it? But that's okay. There's a 2 there. I can just slide that 2 across and it will join that. So that all matches up very nicely. So that's the first thing, is match up the y's. Okay. The next thing is to divide through by anything that remains at the front here. So divide through by x. So I'm going to divide by x, I'm going to divide by x, and I'm going to divide by x. And what that's going to do is it's going to get rid of anything at the front here. And that's what we did last time. We got rid of anything at the front there. And then what we're going to do is we're going to look at this. And that's the thing that we're going to integrate. That's the thing that we're going to integrate. But not only are we going to integrate it, we're going to integrate it, and then we're going to do e to the power of that. So we're going to integrate.
That's f dash x.
That's not our f dashed x. That's our, if you go back here, we called it jx here. We called it jx here. So that it's the jx. It's the thing that multiplies by f of x to give you f dashed x. So it's not.
Okay.
It doesn't matter. It doesn't matter. It won't worry. It won't cause you any problems at all. What you call it isn't going to make any difference at all. So we're going to always, what we're going to do is we're going to integrate this. So we're always going to integrate this. And then after we've integrated it, so we're going to integrate it first, and then we're going to do e to the power of that. So I'll just put that in there then. So that's 3 over x. Okay, so those are the 2 steps I need to do. I need to integrate the 3 over x, and then I need to do e to the power of that. And then that will tell me what I need to multiply by. That will be the integrating factor. Okay, so help me with this. What's the integral of 3 over x, Devansh?
3 ln x.
And what's e to the power of 3 ln x?
So it becomes x cubed.
It does become x cubed. Hold on, let me just catch up with you there. I'll take that 3. And Devansh is saying move the 3 up here. And then the e and the ln will cancel out. And it just becomes x cubed. So the integrating factor is x cubed. What I need to do is multiply through everything by x cubed. So let's scratch that. Now we know the integrating factor. We don't need any of that anymore. The magic has been done. Now we just need to multiply through by x cubed. So multiply by x cubed. So that's going to be x cubed times 2y dy by dx. Multiply by x cubed. But it says 3 over x. If I multiply by x cubed, it's going to give me plus 3x squared y squared equals, and I'm going to multiply this one by x cubed as well. So that gives me x squared e to the x cubed. Okay, let's match things up again. So the y already matches with the 2y dy by dx because we haven't touched that at all. So that's still fine. The x cubed, now it matches. Wow, look at that. It now matches. Isn't that amazing?
Wow.
See, you don't need to go outside to see fireworks on Diwali. This is so much more exciting. I'm not even going to try and defend that.
Is doing the e to the integral 3 over x, is that always how you find the integrating factor?
Yeah, so we'll do a few more examples, and that's exactly how we'd find the integrating factor. You match up the y's, you get rid of anything else in front of the very first term, and then whatever is left out, sticking out on that second term, you have to integrate it and do e to the power of it. And that's exactly how you find the integrating factor. And as I told you, the understanding bit is more complicated than the procedural bit. So to understand what we did is more complicated than actually doing it. Doing it, you'll find it's repetitive. It's the same thing every time. Sometimes in maths, understanding comes later. So you do it, you practice it, you know how to do it, you do it 100 times, and then slowly it starts to all make sense and you'll start to understand it. So there's a lot going on in this question, but we don't need to worry about everything that's going on. Because everything matches now, we can integrate this, and we can say that gives us x cubed y squared. Remember, it's the front of each of the arrows, equals, and then we can integrate this. My guess is going to be e to the x cubed. When you differentiate e to the x cubed, you get 3x squared e to the x cubed. So you need a third in front of there, and then we need a plus c in front of there. Maybe you tidy it up by dividing everything through by x cubed. Maybe you tidy it up by dividing everything through by x cubed. Okay, let's do another example. So use the same thing. First of all, align the terms up how they're supposed to be. Shruti?
So x e to the y dy by dx plus 5 ey equals 3x.
Okay, and then match up the y thing and it's dy by dx. So the e to the y, what does that differentiate to give me?
Ey dy by dx, yeah.
Splendid.
And then 5 and the x.
Don't match up, obviously, because that's what the integrating factor. So what would you like to do now?
So divide by x.
Divide by x.
Yeah.
Divide by x.
And then you have to do e to the power of 5 over x integrated.
Lovely. So the next step is integrate 5 over x. And then after you've done that, do e to the power of x. What is the integral of 5 over x?
Ln x.
5 ln x.
Yeah. Yeah.
5 ln x. And then what is e to the power of 5 ln x?
X to the power of 5.
X to the power of 5. Lovely. So what we now know is we need to multiply through everything by x to the 5. So now we can delete this because we've figured out what we wanted from there. Multiply through everything by x to the 5. So times x to the 5 times x to the 5 times x to the 5. What does that give me, Shruti?
X to the 5 ey dy by dx plus 5 over x to the power of 4.
You multiply by x to the 5, so the x to the 5, yeah.
Oh yeah, yeah, and then and then 3x to the power of 5.
Okay, let's match things up again. The e to the y still matches the e to the y dy by dx, but do the x's now match up?
Yeah.
Yep, splendid. So that matches with that, and that matches with that, and so integrate it.
So 5x and then e to the power of y.
And integrate the right hand side.
So that's half x to the power of 6 plus c.
And then now maybe we'll multiply through everything by 2. No, we won't multiply. Let's just divide everything through by x to the 5. Let's just divide through everything by x to the 5.
Okay. Ey.
You can learn it if you want as well, but I think I won't. I think I'll just leave it there.
So how did you get, before you had 2 and then you crossed it out, how did you get the 2x to the 5 e to the y?
Oh, okay, let's go back. The 2 was just me going to multiply through, whoops. The 2 was just me going to multiply through by 2. So what we did was after we matched it up, it's all perfect now. It's an exact differential equation. So the e to the y differentiates to give you e to the y dy by dx. And the x to the 5 differentiates to give you 5x to the 4. So you want the front of each arrow to integrate it. So e to the y times x to the 5. If you use the product rule on that, you get that. This was just strictly integrating this, add 1 to the power, divide by a new power, which gave you half x to the plus 6 plus c. I was going to multiply through by 2 because I thought it would be better to get rid of the fraction, but then I thought I can't be bothered. It's nice, probably nicer with the multiply by 2, but I just lost interest in it about now. Okay, next one, Joanna.
I think first.
Get the terms in the correct order. So you want the dy by dx term, then you want the y term, and then x only terms on the other side.
Add y squared.
Yep.
So y cot x dy by dx plus y squared.
Did you see that I also put the cot x slightly to the front instead of in the middle anymore? Because I know I'm going to have to start doing this. Is this okay? Does this match up?
You're supposed to have a 2, I think.
Okay, so if I put a 2 in front of there and I put a half in front of there, that's okay, isn't it? I haven't changed anything, have I?
Yeah.
Okay. The x's obviously don't match up because we'll have to do an integrating factor on these ones to make it match up. So the next thing to do is to get rid of this thing in front of the cot x. So get rid of the thing in front of the 2y dy by dx, rather. Get rid of the half cot x. So we are going to divide by cot x and times by 2. So cot x, 2 over cot x times 2 over cot x times 2 over cot x. So that's going to cancel out with that. So it's going to be 2y dy by dx plus, and then that's going to be 2 over cot x, but 2 over cot x is really 2 tan x, isn't it? So 2 tan x y squared equals 2 tan x sec squared x. Okay, let's see if that still works okay. The y squared differentiates to give me 2y dy by dx. It does, but obviously the x's don't match, so we need to figure out the integrating factor, Joanna.
I think, I don't really remember how to do it. I think it was the 2 tan x. You have to do e to the integral of that.
Yep. What is the integral of 2 tan x?
Is it sec x tan x?
No, integral of tan x is...
Oh, ln sin x. I know that's cot x.
Ln sec x. So tan x is sine x over cos x. Your guess would be ln of cos x. But when you guess ln of cos x, that gives you minus sine x over cos x when you differentiate it. And so you have to multiply it by -1. So it ends up being ln of sec of x. So ln of sec of x, but it's 2 tan x, so it's 2 ln sec of x, and e to the power of that. Carry on, Joe.
So then the integrating factor then would be...
No, you need to simplify that.
Oh yeah. So then you would do... you would make that equal to... no, you can bring the power up, so it would be sec x squared, and then the e and the ln cancel, and then becomes sec squared x.
Yeah, so sec squared x is what you need to multiply by. So the magic has been done. We know we need to multiply by sec squared x. So I can rub out this bit of working here and just multiply through by sec squared x. So times sec squared x times sec squared x times sec squared x. And so that gives me sec squared x times 2y dy by dx plus 2 tan x sec squared x y squared equals 2 tan x sec to the 4x. Okay, let's see if everything matches up again. So the y squared, when you differentiate, it gives you 2y dy by dx. That's exactly as we expected it to be. That's how it's always been. And the, what's the differential of sec squared x, Joanna?
Sec x tan x.
No, you have to use the chain rule to
Oh,
differentiate.
integral.
Differential. Differential
Um,
of sec squared x.
Oh, 2 tan x.
So it's sec x all squared. So the 2 comes down, it gives you sec x to the 1, and you need to multiply by the differential of sec x. Do you remember the differential of sec x?
Wait, what did you say? The differential or the integral?
Differential. We're only differentiating at the moment here. This particular stage, we're only differentiating. I'm asking you to differentiate sec x all squared. So that's the chain rule. So the 2 comes down, it gives you sec x to the power 1, and you need to multiply by the differential of the brackets.
Is the differential, is it sec x tan x?
It is sec x tan x. So what does it give you if you bring the 2 down, you
Oh,
multiply by sec x tan x, and you got sec x to the power 1?
it would be 2 sec squared x tan x.
Yay! Exactly what we've got here. Shruti, love the fireworks.
Yay.
Okay, so that's so we're going to integrate this now. So integrating the left-hand side gives us, Jana.
I think it would be sec squared x y squared.
Yep, y squared sec squared x. And we need to integrate this side as well. What's my guess going to be? A lot of people think the guess is sec to the power 5 of x. A lot of people think the guess is sec to the power 5 of x for this integral. Still you, Joanna?
Oh, sorry, I didn't know. It would be 5 sec x tan x times sec to the times sec x to the 4.
Yeah, and what does that all simplify to?
5 sec to the 5 x tan x.
Is that okay?
No.
A lot of people think that the guess is sec to the 5x, and a lot of people are wrong when they think that. A horrible teacher making you do it wrong and then just laughing. Okay. Okay, so sec to the 4 should be the correct guess. So for sec, we don't add 1 to the power, we just leave the power the same.
Is it me again?
The whole
it would
question
be.
is to you.
Oh, okay. It would be 4 sec to the 5. Oh no, sec to the 3 x.
Yeah, yeah.
And then tan x.
No, what's the differential of the inside of the brackets?
Sec x tan x.
So what's the answer?
It would be 4 sec to the 4x tan x.
Okay, and so we need to divide it by 2. So our answer is going to be a half sec to the 4x plus c. We have to put in our plus c before we divide through by sec squared x. So y squared equals a half sec squared x plus c cos squared x. So there's our answer. Okay, so that was another one done using integrating factor. Next one. So now what we're going to do is we're going to kind of cheat a little bit. So what we're going to do is we're going to line up the terms. They're already lined up, to tell you the truth. Then we're going to match up the y with its derivative, dy by dx. And then what we're now supposed to do is we're supposed to divide by sine x. But you know what? We can't be bothered. We don't have, like, it won't matter if we don't. No one's going to notice if we don't. So we're supposed to divide by sine x. What is that going to give us in this term that hasn't already been highlighted? What's that going to leave us with here if we divide by sine x? What's that going to give us here if we divide by sine x?
Cot x.
Yeah, to Shane.
3 cot x.
3 cot x. And so our integrating factor is going to be e to the integral of 3 cot x. So we don't have to divide. What I'm saying is, yeah, you can divide through by sine x. Yes, that's the proper way of doing it. Yes, we should all do it like that. But sometimes we break the rules because we get a bit lazy and we want to find a quicker way of doing it. So I'm just not going to bother dividing through by the sine x because I can do it in my head. I don't actually physically need to do it. And what is the integral of cot x again, Shane?
That's ln modulus of sine x.
Modulus of sine x. And so what's our integrating factor going to be? Shane. You've integrated the 3 cot x, so that gave you 3 ln sine x, and now you just got to do e to the power of that.
Oh, so that's going to...
So this 3, we need to move it out of the way because it's stopping us cancelling the e and the ln. So this 3 is stopping us cancelling the e and the ln. We need to move it out of the way.
Oh, so we bring it down to the power.
And then now the e and the ln just going to cancel each other out.
So it's sine cubed x.
So that tells us not to multiply by sine cubed x. It tells us we need sine cubed x at the front. So it doesn't tell us what to because we didn't divide. If we divided by the sine x, we'd have nothing at the front there. We'd just have a 1 at the front there. And then the integrating factor would be multiplied by sine cubed x. But because we didn't actually divide by sine x, the integrating factor now just tells us what we need at the front. We need sine cubed x at the front. So what do I need to multiply by? To Shane.
Sine squared x.
Times sine squared x. Times sine squared x. Times sine squared x. And so that gives me...
Please, can you repeat that? I don't understand why you multiply by sine squared x and not sine cubed x.
Okay. So, all right. Did I do this properly? What's my next step supposed to be if I'm going to do it properly? I've matched up the y with its dy by dx. What's my next step supposed to be if I'm going to do it properly?
Okay.
You're supposed to get rid of anything in front of that. You're supposed to get rid of anything in front of that. And then the integrating factor is going to be e to the integral of 3 cos x over sine x, 3 cot x, which is going to give us e to the power 3 ln sine x, which is going to give us sine x all cubed. So what we're supposed to do is we're supposed to multiply this by sine x all cubed times sine cubed x times sine cubed x times sine cubed x. What did we do first? We divided by sine x. What are we doing now? We're timesing by sine cubed x. Isn't that silly? That's sort of like making a cake for your sister's birthday. Oh, and your brother's birthday is the same day because they're twins, and then saying, oh, well, I'll now start making a whole second cake all over again for my brother's birthday.
Why not?
Two, huh? You just make two.
Why not the two? Yeah, okay.
Yeah, okay, but fine. Just do double the mixture and make 2 in one go rather than do it in 2 goes. It'll take you. And also, you've got maths homework to do. You haven't got time to be making cakes. Okay, so what I'm proposing is that we skip the step where we divide through by sine x, and we skip the step where we multiply through by sine cubed x, and we combine them into one step. So what I'm saying is, when we get to here, we know that the rules say you're supposed to divide by sine x. But we don't have to do it. We can just do it in our heads. Oh, 3 cos x divided by sine x is 3 cot x. There it is. And now we know we need to integrate that and do e to the power of it to get the integrating factor. And the integrating factor tells us that you should now multiply through by sine cubed x. But remember, there should not be a sine x here in the first place. So if there isn't a sine x here in the first place, and we multiply by sine cubed x, what will we end up with at the front? We'll end up with sine cubed x at the front. So all I'm saying is now, instead of seeing the integrating factor telling you what to multiply through by, because we're cheating, see the integrating factor as telling you what you want at the front, not what to multiply through by, but what you need at the front. You need sine cubed x at the front. Well, you've already got a sine x at the front, Joe. So what are you going to multiply through by?
Sine squared x.
Yeah, and I'm proposing that if you do it the strict lockdown rules, you would divide by sine x and multiply by sine cubed x. And I'm saying, hey, I don't want to do that. I just want to multiply by sine squared x times sine squared x times sine squared x times sine squared x, which will give me at the front sine cubed x. Sine cubed x. dy by dx. That's what this is trying to tell you. You must have sine cubed x at the front. That's what it's trying to tell you. You must have sine cubed x at the front. And I've got it. Plus 3 cos x sine squared x times y equals 2 sine squared x. Let's match up the y with the dy by dx, which matches up. Let's match up the sine cubed x with the 3 cos x sine squared x, which is correct. That's the differential of sine cubed x. So that matches with that. And the sine cubed x differentiates to give you 3 cos x sine squared x. Everyone knows that's true. And so now if I'm integrating the left-hand side, I'm going to get sine cubed x times y. And if I'm oh crap, how do I integrate 2 sine squared x? I've forgotten how to integrate that. Don't you have to replace it with something? Don't you have to replace the sine squared x with a half something plus something? Was it half something minus? I can't remember. How do you integrate sine squared x? Remind me again, Tree.
You replace it with half cos.
No. Jen?
It would be a half sine
Oh,
half x
Jane.
cos half x.
So sine squared x, whenever you want to integrate sine squared x,
Oh, it was just lens.
Oh wait, I did the double angle formula.
it is from the double angle formula. You replace it with a half brackets 1 minus cos 2x. And you lot should know that by now. A half brackets 1 minus cos 2x. And if you don't know it by now, tattoo it on your forehead. You know what I did with one of my students once, years ago? This is Chirag Patel. So he'll remember it if you were to ask him. He's all grown up. He's got kids now to go and everything. Because he didn't remember this when I asked him, I got a marker. So I was a one-to-one student, so I was sitting right next to him. I got a marker and wrote it on his forehead in mirror writing, so that every time he looks in the mirror, he would say, and I told his parents he's not allowed to rub it off till the next day. So he had to go.
Is that a skill of yours? Can you just write in mirror writing on command?
Not particularly, but it wasn't a long thing to write in mirror writing, so it was all right. It was a bit rubbish, but it is readable. And he had to go to school the next day with that written on his forehead. And his parents said he went. I know. I used to be really cruel. I don't know. Like I feel embarrassed by how cruel I was in the old days. Okay, so but we've got 2 sine squared x. So we're going to replace it with 1 minus cos 2x, and then integrating the 1 gives us x, and integrating the minus cos 2x gives us minus a half sine 2x, and then we need a plus c. Okay, so there's our answer. It's a bit messy, but it's okay. It's fine. Okay, we're a little bit bored of these now. Oh, this one looks quite easy. That looks quite easy. So let's
There's 2 y's.
Yeah, there's a y term and another y term. We could divide through by y. Y. That would fix it. Or we could minus the y and then minus the y out.
Yeah.
Or, and this is kind of mean of me, we could ask ourselves, hold on a second. What we're supposed to do is we're supposed to, first of all, use the method we learned in A-level maths, and then use the method we learned in further maths. So can we do this by separating the variables? Can we do this by getting all the y's on the dy by dx side and all the x's on the other side? So dy by dx plus 3xy, no, sorry, plus 2y minus 3xy plus, oh, hold on, equals. I'm moving it to the other side. Equals 2y minus 3xy. dy by dx equals y brackets 2 minus 3x. 1 over y dy by dx equals 2 minus 3x. Integrate both sides. Integrate and take the dx up here. So basically all I'm doing is saying, yeah, but don't be tricked. Don't be tricked into using the more complicated integrating factor method if you can separate the variables. Number one is, when you see a first order differential equation, the first thing you do is, can I separate the variables? If you can separate the variables, do it that way. If you can't, then you need to use the more powerful techniques that we're learning in further maths. Yeah, so just reminding you of that. Okay, there's a lot of these examples, isn't there? Okay, Foldy WCC. Foldy WCC is an acronym for first order linear differential equation with constant coefficients, which is these. First order linear differential equation with constant coefficients, which is these. So you're not allowed to have an equation with x's in it there. You're not allowed to have an equation with x's in it there, but you can have an equation with x's in it here. So these are really quite simple things. I've restricted things so much to try and produce a really simple equation. And now these are things that we can already solve. We can already solve these. We can solve these by using the integrating factor method that we've learned just now. But actually, to tell you the truth, we could solve these by using separating the variables as well. So we can already solve these ones. And so all I'm doing is saying, let's find a quick method. Because we already know how to solve these, let's find a new quick method. And the reason for the new quick method actually isn't so that we can solve first order linear differential equations with constant coefficients, because we can solve them anyway. It's so that when we move on to second order linear differential equations with constant coefficients, the method will be compatible with this method. And so we're just learning it to get some practice in of something that we're going to be doing later on. And so the method that we're going to use is called the CF plus PI method. The CF plus PI method. And I've said to you, look, we can already solve this using an integrating factor. We can already do this using an integrating factor. What I'm now going to do is I'm going to try and learn this new method. CF stands for complementary function. Complementary function. And PI stands for particular integral. And the method basically splits the answer up into two separate sections. So it splits the answer up into two separate sections. So what I've done is I've taken this differential equation here and I've basically scratched out this. I've made it disappear. I've just put a 0 on the other side. And by putting the 0 on the other side, this becomes really easy to solve. I mean, this you don't even need to use the integrating factor to solve this. You just do dy by dx equals minus 2y. Then you divide both sides by y. 1 over y dy by dx equals minus 2. Then you put an integral in front of both sides. Integral, integral. And then that gives you ln y. I'm not going to bother with my constant. Equals minus 2x. And then e to the power of both sides. So y equals e to the minus 2x. Oh, I didn't put in my constant. Let's put in my constant. A is there. That's going to give me an A, but then by the time I've divided by 8, I'm going to call it C. So the solution to this differential equation is simply y equals c e to the minus 2x. Y equals c e to the minus 2x. Okay. Oh, I've given you a different one. I've changed it to dy by dx plus ky equals 0. So it's no longer a 2 at the front there, it's a k at the front there. But I'm
Just
sure you...
replace the 2 by k.
Say that again, Shruti?
Just replace the 2 by k.
Yeah.
So c e to the power minus k x.
Perfect. Perfect. Excellent. Oh, okay, then this one. I don't know why I've done another one.
Shut.
Is that your brother, Shruti? He sounds little.
So it's very little. Do you want to say hi? Do you want to say hi? Wave to the camera. Say
Hello,
hi.
Shruti brother. How are you?
Do
You
you wanna
alright?
he can't really hear you because do you want
Oh,
to
you
say
got
hello?
headphones on.
Hello.
Hello. Hiya.
What's going on? How are you?
How are
Hi.
you?
I'm very well. How old are you, Shruti's little brother?
He asked how old you are. Can you not hear?
I'm 7 years old.
Oh, wow, you're quite big for 7 years old. You're about the same size as Shruti, aren't you?
A bit taller. He's saying you're very big for a 7-year-old.
I'm really big for 7 years old.
Yeah,
Okay,
he just
right.
said that too. Okay.
Okay.
You can leave now. Bye.
Does he know how to use earphones yet?
I don't think he put it in the wrong way. I don't think he knows.
Minna had this problem. She said the earphones don't go in ordinarily anymore. They go in like upside down or back to front or something. She was saying,
Or she ran it the wrong way around or something.
yeah, she had some problem with the iPhone earphones because they go in like backwards or something like that. I don't know.
For me, the new ones don't fit in my ear for some reason. I think I have a weird ear shape. It's only the older ones that are like round. I don't know.
You can
Yeah.
get ear enlargement surgery for that. So yeah, just save up. Tell your dad you want some ear enlargement surgery, and then the iPhone buds will fit you all the time. And then
Yeah.
otherwise, it's going to be a constant problem, Shruti.
Yeah, I mean, it makes sense to get spend loads of money on surgery and then pay extra for the new earphones. Yeah.
I thought you were like the generation who is quite okay about cosmetic surgery and stuff. My generation hates that concept. We associate it with vanity, and we don't like vanity at
Oh
all.
no, I think it's just me. I just get scared of needles. I don't know why. I made a big deal about my vaccination with needles as well. I can't. Yeah.
So that's what Menna does.
She's
Oh my
scared of
God,
needles.
She starts crying and everything, and then they have to pin her down, and they have to have 3 nurses, and they have to pin her down, and yeah, so it's terrible. Okay, so what about this one then, Devansh?
So would that be c equals a half e to the half x?
E to the minus a half x.
Minus a half x, yeah.
Okay, so if you see something like that, it should be easy to figure out what the answer is. Okay, so one more. To Shane.
CE to the power 5x.
Lovely. And if you didn't know, what you'd do is you'd write dy by dx equals 5y, and then you divide by the y, and then you'd say integrate both sides, and you get 1 over y equals 5x, and then e to the 5x is your answer. And then there's got to be a constant, so you just put c in front of it. It doesn't make any difference. Okay, so what I did was I scratched the 3x off of here, and I said that the answer for this is y equals ce to the minus 2x. But I cheated. I scratched the 3x off, called it 0, then I did this, then I said the answer is ce to the minus 2x. Is that an acceptable thing to do? Heh.
No.
No, you can't just scratch off the right-hand side of an equation and then say, yeah, I've solved the one where I disappeared the right-hand side of the equation. So we know that if I put that back as 3x, it's not going to be this answer. But it turns out it is going to be this answer plus something else. It is going to be this answer plus something else. So although I scratched off the 3x, which you'd think would completely change the answer, it doesn't completely change the answer. It only slightly changes the answer. And we can do it by scratching off the 3x, working out what the answer would be without the 3x, and then working out what the answer would be with the 3x, and then somehow combining the two together. And I'll show you what I mean. So I want to solve this now. And what I'm going to do is I'm going to do it in a kind of weird way. I'm going to say we've got some function, which is effectively y. We're going to multiply it by 2, and then we're going to add on f dashed x, which is dy by dx, and the answer's got to be 3x. So some equation, we don't know what it is, multiplied by 2, plus the differential of that equation has got to equal the 3x. Now, I propose that the equation must be e to the x. I propose that the equation must be e to the x. So I'm saying when you take e to the x, times it by 2, add on the differential of e to the x, that is likely to give you something like 3x. I might just be talking utter nonsense. So I propose that fx is e to the x. Do you concur, Joanna? Or do you disagree?
No, I think it's it makes 3x.
It's the answer. When you take whatever the equation is, multiply it by 2, add on the derivative of that equation, the answer's got to add up to 3x. But you don't have to get the exact answer straight away. You can say, okay, well, my answer doesn't add up to 3x. My answer adds up to 2x. We can fix that later on, or, you know. And I'm just saying, what form should fx be?
Could be...
I think it should be like e to the power x, or like, you know, a e to the power x, some multiple of e to the power x.
Then if you do e... No, because if you do e to the power something,
yeah,
you'd get...
You'd never get a 3x. You'd end up with loads of e to the x's in there. Okay, I've changed my mind then. I think fx is sine x. I think sine x, when you multiply it by 2 and you add on the derivative of sine x, it gives you 3x.
No.
Oh, I thought you were going to say yes, Het, but don't worry about hurting my feelings. Okay, Shruti, I've changed my mind. I think it's a quadratic. I think fx is a quadratic. You're going to multiply it by 2, and you're going to add on the derivative of fx, and that's going to give you 3x.
I think it should be x.
You think
Shouldn't
it
it
should
be
be
x?
linear, not quadratic?
Yeah. Yeah.
Linear. Okay, so Shruti says it should be linear. Let's try Shruti's thing. Linear would be something like ax plus b. And we've got to multiply it by 2. And we've got to differentiate the ax plus b. Differentiate ax plus b is just a. And the answer's got to equal 3x. So in other words, 2ax plus 2b plus a plus 2b plus a has got to equal 3x. In other words, 2a has got to be 3. So a has got to be 3 over 2. And if a is 3 over 2, let's replace the a with 3 over 2. 3 over 2. Then 2b plus 3 over 2 has got to be 0 because there's no units term at the end here.
Minus 3 over 4.
So b has got to be minus 3 over 4. So an equation that works in here is y equals 3 over 2x minus 3 over 4. Minus 3 over 4. That works if you put it in as y. Let's check it. Let's check it. I don't want to have made a mistake and not realize it. Let's check it. So y is going to be equal to 3 over 2x minus 3 over 4. So 2y is going to be 3x minus 3 over 2. So there's 2y. Plus dy by dx, plus dy by dx. Dy by dx is just going to be If you differentiate that, you get okay, thanks for the help, guys. 3 over 2 equals 3x. Does it work? Does it work? Does it work? Come on. Can we have some like simultaneous cheering or rapturous applause or something like that? It does work, doesn't it?
Yeah.
Okay, thanks. So what we've learned is if you put y is 3 over 2x plus 3/4 into this equation, it does give you 3x. Now what I'm going to propose is a bit weird. The answer to this, we know from before, was y equals ce to the minus 2x. We know when you put that into there, it gives you 0. So if you take ce to the minus 2x, you multiply it by 2, so that's going to give you 2ce to minus 2x. And then you also differentiate it. Differentiate it is going to give you minus 2ce to minus 2x. And you add the two together, it gives you 0. It does. It gives you 0. It does. And we knew that by guesswork, by nothing more than guesswork, by nothing more than experimental kind of, you know, let's try it and see, we know that y equals 3 over 2x minus 3 over 4 works. If you put it in here, if you multiply by 2, you get 3x minus 3 over 2, and you differentiate to get 3 over 2, you add the two together, it gives you 3x. And so I'm going to propose that the solution to the equation dy by dx plus 2y equals 3x is actually this. Is actually y equals ce to the minus 2x plus 3 over 2x minus 3/4. Now you can see where I got them from. You can see where I got them from. You can see that that is from there, and you can see that that is from there. But am I justified in making this statement that this will still work? This whole thing here will still work when you put it back into the differential equation. Am I justified in making that statement? And if I am, how comes I am?
Yes, because
you know, when you do differentiation, you kind of do it one term at a time. So if I'm doing something like differentiation of, like, you know, y, oh, it's not a good pen to use, y equals x e to the x minus 4 over x plus 2 squared minus 2 sine x. That's a hyperbolic function, which you don't know. Okay, so ready, we're going to differentiate this. So dy by dx equals, differentiate the first one, should we?
So x times ex.
Yeah.
And then plus ex.
So you just started using the product rule, no worries whatsoever, even though you know you're not going to be able to differentiate this one because we haven't learned about hyperbolic functions yet.
Yeah.
The reason is when you're differentiating this one, you're not looking at that one. You don't care about that one when you're differentiating this one. So the same sort of thing applies here. So when I want to put this back into the equation, I can, of course, try and treat it like one thing, but I could also put it back in a piecemeal way. So when I put this bit back in, and I'm going to put it into here, and I'm also going to differentiate and put it into here, what will happen when I do that? When I put this in here and differentiate it and put it in here, and then add it all up, what's it going to give me? Should be
3.
What's it going to give me?
I don't know what you're asking.
So here's my final answer. My final answer for this differential equation is y equals ce to the minus 2x plus 3 over 2x minus 3/4.
Yeah.
Although that's my final answer, I've got it in two pieces. The first piece is CE to the minus 2x, and the second piece is 3 over 2x minus 3/4. So I'm going to start with this second piece. I've switched now. I'm going to start with this second piece. If I put that back into here, if I put this second piece back into it, so this is my answer. So if I put it back in, it should work. So if I put that back in there as y, then you're going to get 2 lots of 3 over 2x minus 3/4. What is 2 lots of 3 over 2x minus 3/4?
3x minus 3 over 2.
Lovely. And also you're going to put it back into here, which means you've got to differentiate it first to put it back into there. What's the differential of that?
So 2x squared.
The differential of this, the differential of this, the differential of this, the pink bit, the differential of this. Just differentiate. Just differentiate.
3. Yeah, so 3x.
Differentiating, not integrating. Differentiating, not integrating.
Oh, 3 over 2.
3 over 2. So we get, when you put this in here as y, you got 3x minus 3 over 2 when you doubled it. And then you got here plus another 3 over 2 when you differentiated it. So you got 3 over 2x minus 3. Sorry, you got 3x minus 3 over 2. You got 3x minus 3 over 2. And then you got plus 3 over 2.
Oh, so that's just, okay, you get the same.
So you get 3x. But now we also need to put this in. Now we also need to put this in as well. Into here and into here.
So into the x.
So into as y. So y is going to be CE to minus 2x. So 2 lots.
Yeah. 2 CE.
And then also differentiate this.
So minus 2 CE to the power minus 2x.
So you got minus 2 CE to the minus 2x plus 2 CE to minus 2x.
It cancels out.
So it gives you 0. It doesn't give you 3x.
Yeah. No.
But does that matter that it doesn't give you 0? Because this bit's already giving you 3x.
Oh yeah.
So the whole thing works to give you 0 plus 3x, and that is 0 plus 3x. If I write this as 3x, plus 0, and I highlight the 3x as being pink and the 0 as being blue, then this bit here, the 3 over 2x minus 3/4, goes into the left-hand side and delivers you the 3x. And the CE to the minus x goes into the left-hand side and delivers you the 0. And so the answer is this one here. Somebody who puts in this answer isn't fully making use of their baggage allowance. Do you know what fully making use of your baggage allowance is? Okay, so Shruti, if you go to India, and this is true, I know this is true. If you go to India on a visit, right, what will happen is you'll pack your clothes to go to India, and you'll pack 2 pairs of jeans and 2 tops, yeah, and maybe a few pairs.
Am I going for like 2 days?
No, for like
I'll go for more than 2 days.
A month.
Okay, right.
What clothes do you need? You're probably going to buy.
I pack a bit more than that. Yeah.
You're going to buy clothes when you're in India, so you're not going to carry too much. And then what's going to happen is your grandma's going to see how empty your suitcase is, right? She's going to say, she's going to pick it up. She's going to say, that's nowhere near 25 kilos. You're allowed 25 kilos. That's only 5 kilos. And then what she's going to do is stick in tins of baked beans, like 100 tins of baked beans into your suitcase. And then you're not going to be able to lift up your suitcase. And you're going to go, Grandma, why have you stuck in 100 tins of baked beans? And she'll say, because in India, you cannot get Heinz beans. You cannot get the Heinz beans in India.
My mom does that with celebrations. Like celebrations.
Okay. I knew when I went down the Heinz beans route, it was probably going to turn out wrong, because that's not the thing that you can't get in India and that you're desperate to get in India. But I know that there is something that you I just wasn't sure what it was. Yeah. So that's your free extra allowance. You can carry it through for free. So why wouldn't you? So yes, this bit here, if you put it into there, you put it in instead of the y, and you differentiate it and you put it instead of the, you get 3x. Yes, you get 3x. But if you also carry that in with you as well, it doesn't make a difference, because that gives you 0 when you do it in there. So it goes through for free. Yeah. And so these two together make a better answer than just one of them on their own. So that's going to take a little while for you to fully grasp. Okay, so what we're effectively saying is the answer is made up of two bits. This bit here is called the complementary function, CF. It's complementary. When you go on the plane and you ask them, can I have a Coke? And then you bring out your £2 for the Coke. They say, no, it's complimentary. You don't have to pay for the Coke. It's complimentary means it's free. It goes through for free. And this is called your particular integral. Particular integral. It's the integral that you know works. It particularly works. This bit goes in for free, and on its own, you can't do it. You know those 100 tins of celebrations? Your gran can't go to the airport and just say, I've got 100 tins of celebrations. I'm not flying to India, but can you take them for free for me? Because if I was, I'd be able to fit them in my suitcase for free. That doesn't work like that. It's only if you've already got this one going to India that you can throw that one in for free. Okay. That's a really weird analogy. Okay, so here we go. We want to solve this type of differential equation. So what we're going to do is we're going to say, this is our differential equation. We're going to say, if you imagine it's dy by dx minus lambda y equals 0, this is called your complementary differential equation, your CDE, your complementary differential equation. You just scratched off the fx off the end. You just scratched off the 3x off the end, and you just called it 0, yeah? When you solve this, the answer will always be the same. It will be y equals ce to the lambda x. It's always going to be that. It's going to be easy to work out. Okay, so that's the complementary function. That's the complementary function. That's the complementary function. Our answer is going to be the complementary function plus the particular integral. Well, what's the particular integral? Well, the particular integral is different. The particular integral is now you're not allowed to scratch this off anymore. But what you've got to do is you just got to use a bit of guessing game. You got to play a little guessing game. You got to say, right, what equation would y be if I multiply it by 2 and I differentiate it and my answer is 3x? And the answer would be, it would be linear. Y would be linear. Y would be linear. Y would be, I didn't want that. Y would be ax plus b. Because when you put in y as ax plus b, you get a linear if you multiply it by 2. When you differentiate a linear, you get a constant, and a linear plus a constant gives you a linear, and that's a linear there. Okay, so now we're going to learn the rule for what should the guess be in every case. So what should the rule be in every case? So fx here refers to this. If fx is 3x, then your particular integral is going to be of the form ax plus b. If fx is 3x plus 2, in other words, some multiple of x plus some number, your guess is still going to be ax plus b. If fx is a quadratic, if it's 3x squared, then your guess is going to be ax squared plus bx plus c. If fx is an exponential, if it was, let's cross out that, and let's say it's e to the 2x, let's say it's 3e to the 2x, then your guess is going to be ae to the 2x. You're still going to use the 2x because that's going to stay the same, but you're going to put an a in front of there because it's not necessarily going to stay as a 3. If this isn't that, if it's 2 cos x, then your guess is going to be a cos x plus b sine x. And if it's 2 sine x, then your guess is going to be the same. It's going to be a sine x plus b cos x. And if it's 2 sine x plus 3 cos x, your guess is still going to be the same. It's going to be a cos x plus b sine x. This table, you'll see it next to every single question that we do. You'll see it next to every single question that we do. But eventually you'll have to understand the table and know the table. You'll understand the table and know the table because when you do the example, slowly you go, yeah, but that's obvious now. Yeah, but that's obvious now. So it'll become obvious to you in a little while. Okay, so let's see. So initially we're going to use the table. So let's start off by getting rid of this. So this is our complementary differential equation. This is our CDE. C, D, E. And that gives us our complementary function. So our complementary function is going to be y equals c e to the 3x. If that's a minus 3, that's just going to be a 3. That's it. Nothing more complicated than that. Not hard. Okay. So that's going to be our complementary function. Okay, so that's the complementary function done. Now we need to do the particular integral. So now we need to do the particular integral. And in particular, we're not actually going to work out the particular integral. We're just going to say, what form would it take? So what form would it take? And so we're looking at this function here. And we're seeing in this list of functions, which one does it match? Which one is it closest to matching?
Ax squared plus
bx plus c. So our particular integral is going to be y equals ax squared plus bx plus c. That's going to be our particular integral. Now we won't know a, b, and c, and we'll need to figure them out, but that's how we're going to do it. Our particular integral is going to be y equals ax squared plus b. And then what we'll do is we'll add these two together, and we'll say, once we found the a, b, and c, we'll say y equals c e to the 3x plus ax squared plus bx plus, I can't use c because I've already got a c there, so I have to change that to a d. And we'll know a, b, and c by then. We'll know them, so we'll just be able to put in their numbers, and then that will be our general solution. Okay, we're just going to go to the particular integral this time. What type of particular integral will I need in this case? Which one does it match in the table? What type of particular integral will I need in this case? My particular integral would be y equals what? And I'm asking that to Shane.
A e to the px.
A e to the minus x. You notice that p is exactly the same as that p. In other words, if yours is minus 1, then this will be minus 1. Yeah, you don't need to put an unknown in there. Why? Because when you differentiate e to the minus x's, it just gives you e to the minus x's. The powers don't ever change, so you don't need to worry about changing that. Yeah. Next one. What will be the form of the particular integral in this case? And I'm asking that to, so particular integral is going to be y equals, which one of these is it going to be? And what do I need to write down here? I'm asking that to Devansh.
That would be a cos 3x plus b sine 3x.
Smashing, wonderful. There's no point in changing the 3 because when you differentiate cos 3x, the 3 never changes. When you differentiate cos 3x, you get minus 3 sine 3x. The 3 doesn't go away. So the 3 next to the x doesn't go away. So that's why we've kept those as 3. Next one. Oh, just a 7. Oh, just a 7. What form should my particular integral be here?
7.
Not 7. When this is a number a, then this will be a different number a. That a and that a, they're not the same letter. So a, not 7, but just a number a, which might be 7, but probably won't be 7. Next one. Okay, it says now start solving them. Okay, so now it actually wants us to solve them. Oh, okay, all right, fine. Now it actually wants us to solve it. So, okay, so, well, let's do it. We know how to do it. What were the colors? I like the color coding thing. I like sticking to color coding. Okay, so I can't tell what the colors were. Particular integral is green and complementary function is pink. Okay, so complementary function is pink. So let's start solving it. Okay, so let's scratch this off. Let's scratch off. Let's call it 0. Then the complement, oh, pink. Then the complementary function is y equals c e to the 3x. Done. Complementary function done. That's a minus 3. So that will be a plus 3. Easy, easy, easy. Okay, now we're ready to do the particular integral. So I will change to green. I'll rub this out as well because now we need that in there. What form is my particular integral going to take? Oh, we answered this already, so you already know the answer, but just reiterate it for me, Joanna.
Plus ax squared plus bx plus c1.
Lovely. So pen y equals ax squared plus bx plus c. Okay, so that's the particular integral, but we need to find the a, the b, and the c. That's our job, is to find the a, b, and the c. And the way we do that is by putting this into here. Now, I have a very specific way of doing it. What I do is I write down dy by dx equals, and then I ask you to differentiate this. Differentiate that for me, Joanna.
2ax plus b. Plus. Yeah.
That's it, isn't it? 2ax plus
Yeah.
b. Then I ask you to give me minus 3 times y. Minus 3 times that. Minus 3 times y equals. Let's switch to Shane.
Minus 3a x squared minus 3x minus 3. C.
So minus 3a x squared, minus 3bx, and minus 3c. So everything's got to be multiplied by minus 3, yeah? So minus 3, okay. And now, what I'm going to do is I'm going to add these two together. I'm going to add these two together. dy by dx minus 3y. And when I add it together, I know it's got to equal x squared minus 1. So x squared minus 1 has got to equal. And do you see how I was very careful to line them up? The b and the 3 minus 3c are underneath each other because they're units. And the 2ax and the minus 3bx are underneath each other. So that gives me minus 3ax squared plus brackets 2a minus 3b lots of x plus b minus 3c is the units. So it's very easy for me to add them together because of the way I nicely laid it out. I nicely laid it out with the minus 3ax squared first, and then the 2ax here, and then the minus 3bx, so that gives me a 2ax minus 3bx, and then the plus b and the minus 3c and the plus b minus 3c. So it's, you know, I'm doing it neatly so that whoever's marking it can see what's going on really nicely. And then now all I'm going to do is compare coefficients. So what's the number in front of the x squared here? Well, it's a 1 in front of the x squared. And what's the number in front of the x squared here? Well, it's a minus 3a. So minus 3a has to be 1. Has to equal 1. And so a has got to be minus a third. Okay, so I know a is minus a third. So I'll put that in there. Minus a third is a. And then also I'll put that into there. So that's going to become minus 2/3 because that's 2a. Okay, what's the number in front of the x here? Well, there's no x here at all. So the number in front of the x is 0. And what's the number in front of the x here? And again, they've got to match up. So the minus 2/3 minus 3b, so minus 2/3 minus 3b has got to equal 0. The number of x's on the left has got to equal the number of x's on the right. There's 0 x's on the left, and there's minus 2/3 minus 2b lots of x on the right. Okay, so let's times everything through by minus 1. 2/3 plus 3b is equal to 0. 3b is equal to minus 2/3, and b is equal to minus 2/9. So b is minus 2/9. Let's shove that one in there. Minus 2/9 is b. Minus 2/9 is b. And let's shove it into there. Minus 2/9 is b. Okay, now the last thing is let's compare the units terms. The units term here is minus 1, and the units term here is minus 2/9 minus 3c. So minus 1 is the units term on the left-hand side, equals the units term on the right-hand side is minus 2/9 minus 3c. Again, I can multiply through by minus 1. And then I can minus 2/9 from both sides. So 7/9 equals 3c. And then I can divide both sides by 3. And so that gives me 7/27 is c. And so that gives me plus 7 over 27. And so there is my particular integral all nicely worked out. And now my final step is to join them together. My general solution is y equals my ce to the minus 3x plus minus a third x squared minus 2/9 x plus 7 over 27. Okay, so there's my answer. There's my final answer to the whole thing. And it will have a constant in it. First order differential equations always have one constant in it. And I'm going to show you how to check it as well in a second. I'm going to show you how to check it. We can check this, and we need to check this because you can see the procedures become quite long. So it's easy to make a mistake. Okay, let's do another example. Okay, so dx by dt equals 2x. So dx by dt plus 2x equals t. And then they've given us some numbers to put in. Okay, so that's fine. We can put them in at the end and work out things. You notice they've tried to change it from dy by dx to dx by dt, thinking that that's it. We're going to be totally baffled because they changed it to dx by dt. I don't think that's going to make any difference to us whatsoever. We'll know exactly what we're doing. So the first thing we've got to do is the complementary differential equation and the complementary function. So we scratch that out and change it into a 0. And so our equation is our complementary function is going to be y equals c e to the minus 2x. Because that's a plus 2, so it's just going to be y equals minus c e to minus 2. Did I do that right?
Yes.
Oh, Shruti, it's x. dx by dt is not dy by dx. It's x equals c e to minus 2t. They changed it. X is now y and
I don't see that.
Okay, so let's just change.
You have to change the x to a t.
Yeah. So they've just done it as instead of dy by dx, it's dx by dt. So that's going to be x and that's going to be t. Okay. All right. So that's not going to trouble us. That should not trouble us. Okay. Okay. Now we've got to do the particular integral, and for the particular integral, we've got to look at this, and it's going to tell us which one it is. And of course, these are all x's. You just got to imagine they're all t's now. Yeah. Got to imagine they're all t's.
At plus b.
At plus b. So the particular integral, which is green, if I remember rightly, the particular integral is x equals at plus b. Okay. So what we're going to do is we're going to do the same way as before. The 2x we're going to replace. Oh, let's do it. Let's do it. Yeah, let's do it in this order. It's nicer in this order anyway. The 2x is this 2x. We're going to replace that. So that's going to be 2 times that. So that's going to be 2at plus 2b. Then we need the dx by dt. So dx by dt, which is the differential of this. It should just be a plus a. And those two have to add up. Those two have to add up to t. They have to add up to t. So t has got to equal 2at plus 2b plus a. And then all we're doing is comparing. So we'll compare the coefficients of the t and we'll compare the units. Let's just put a plus 0 in the end there, if that helps. Plus 0. And then we'll compare the units terms. So the units terms is 0 here and 2b there. Okay, so that tells us that 1, which is the number in front of the t, has got to equal 2a. So 1 equals 2a. And so that tells us that a is a half. Okay, now that we know a is a half, we can change that for a half. And then that's a 0. So that's got to be a 0. So 2b plus a half has got to be 0. So 2b has got to be minus a half. So B has got to be minus a quarter. And so the equation is A is going to be a half and B is going to be minus a quarter. So a half and minus a quarter. And then all we're going to do is plonk these two next to each other. So this one and this one just plonk together becomes our general solution. So our general solution is x equals ce to the minus 2t plus a half t minus a quarter. Now they tell us some more stuff. They tell us when t is 0, dx by dt is 0. Now we can't put that into there because, I mean, dx by dt we can put into there and t we can put into there, but there's no unknowns in that equation. So unfortunately, if we want to put that in, we're going to have to differentiate this to put it in. So we're going to have to differentiate this to put it in. Okay, so let's differentiate this. So dx by dt equals minus 2ce to the minus 2t plus a half. And they tell us when t is 0, dx by dt is 0. So t is 0, dx by dt equals 0, minus 2c. That's going to be e to the 0, but e to the 0 is 1 plus a half. 2c equals a half, c equals a quarter. We figured out what c is. C is a quarter. So we can replace the c with a quarter. Okay, now we want to check this. Okay, so how do we check it? It's kind of a bit of a, it's not a quick check. Okay, so what we're going to do is we're going to pick a random number and we're going to pick 1.2. I bet you're surprised by that random number. T equals 1.2. What we're going to do is we're going to work out x and we're going to work out dx by dt, and we're going to do them both on the calculator. We're not going to do any work ourselves. So we're going to do 1.2 store as the calculator forces us to store it as x, doesn't it? So I'm going to have to store 1.2 as x. So x is obviously t. When you do it on the calculator, x is going to have to, t is going to have to be replaced with x. So okay, now I'm going to do the d by dt first, and I'll show you why I'm going to do it that way around. So I'm going to use your d by dx button. So I'm going to use the d by dx button, and then I'm going to type in this button, this equation, which is a quarter 1/4. Oh, hold on. Oh yeah, I did that. I already stored x as 1.2, didn't I? I'm going to type in a quarter e to the minus 2t, e to the minus 2x, e to the minus 2x, plus a half x, plus a half x, plus a half x minus a quarter, minus a quarter. Okay, so that's the equation. And I want to put in 1.2 in the little box at the end because I want the gradient at 1.2. So I'm going to put in 1.2 in the little box at the end. I want the gradient at 1.2. So now I've typed in that same equation that we've got there. Obviously, replacing the t's with x's because of the way the calculator works. And at 1.2. And so it's worked out the answer for me. Whoa, what did I get a syntax error for? Oh, I put in the 1.2 in the wrong place. 1.2 is at the end. The 1.2 is in the little box at the end. Okay, so it's worked that out for me. It's 0.45464. That would be enough. Okay, now I also want to put it in this equation. The reason I did the differential first is because now I can cleverly replay using the replay button. That's the up arrow, which takes me back to the same equation. So, or press the down, oh, hold on, press the AC and then press the up arrow. I don't know, press the AC and press the up arrow. Don't press the on button because then you'll lose everything. Did you get back to the same equation? Press the AC and then press the up arrow.
Oh, yeah.
Okay. Now I'm going to press the forward arrow. The forward arrow is going to take me to the front of that equation. My little cursor is going to be in front of the d by dx. And then I'm just going to press delete. Just delete, nothing more than delete. And that leaves me with the equation. I don't have to retype it in. Woo! And then I'll press equals. And then it will put that in and it will tell me that x is 0.37268. Now I'm going to take these numbers here and I'm going to plonk them into here. dx by dt plus 2x should equal t. Well, I know t is 1.2 because that's the value I chose. T is 1.2. I know dx by dt is 0.45464, 0.45464, and I know x is 0.37268 plus 2 lots of 0.37268 equals, and if that works, it means my working is correct. So 0.454, I can't read that anymore.
64.
Okay, 45464, 45464 plus 2 lots of brackets. What was the x? I could have just used answer. I can still just use answer. 2 lots of answer equals, and it gives me 1.199999999, which is 1.2, which is 1.2. And so that checks it. And so in the exam, I'm going to shout, yes, I got question 3 right out aloud, and I'm going to skip around the exam room twice to show that I've got the question right. It's important to let the other people in the exam room know that you've got that question right. It gives them confidence as well. So, yeah. Okay. Okay. All right. Failure case. Failure case. Okay. So let's scratch off this. Call it 0, and then our complementary function is going to be y equals ce to the minus 7x. That's going to be our complementary function, but we need to do the particular integral. So let's unscratch that off and let's look at this and see which one it matches. And tell me what form our particular integral should be.
AE to the power of minus 7x.
AE to the minus 7. Okay, that can't make sense. And I tell you why that can't make sense. Because that and that are the same. Whether you change the A to a C, it makes no difference. They're the same. It wouldn't be a different thing. So that's called the failure case. When the complementary function that you've already worked out, and then the particular integral turns out to be the same as that. And if that's the case, then you can't use that as your particular integral. So what happens now? Unfortunately, things go messy now. Things go really messy now. What you have to do is you start scrabbling around for other guesses for particular integrals. So yes, the particular integral is still going to be something like y equals ae to the minus 7x, but it can't be ae to the minus 7x. So it could be ax e to the minus 7x, or it could be ax plus b e to the minus 7. It's going to have a e to the minus 7x in there, but it's going to have to be more complicated than just having an a in there. It's going to have an ax in there or something like that. And you're going to have to do it until you find one that works. There's no shortcut for it. You're going to have to do it until you find one that works. So I think this might work. I'm going to try this one, and then that's more complicated. So if this fails, then I'll try this one. So let's try it. Okay, so do the same thing as before. What's 7 lots of y? What's 7 lots of y? Well, y is going to be ax. Y is going to be ax e to the minus 7x. So 7 lots of y is going to be equal to 7ax e to the minus 7x. Okay, but now I've got to differentiate it. Oh dear, that's not as easy as it used to be. Okay, so differentiate the first one, multiply it by the second one, so that gives me e to the minus 7x, plus differentiate the second one, multiply it by the first one, that gives me minus 7ax e to the minus 7x. Had to use the product rule for that. Okay, so dy by dx is, well, it's minus 7a x e to the minus 7x minus 7a x e to the minus 7x plus a e to the minus 7x plus a e to the minus 7x. And then I'm going to add these together like these two. I'm going to add these two together like this one and this one is this one and this one. And I'm going to add them together and make it equal to e to the minus 7x, equal to e to the minus 7x, equal to e to the minus 7x. And what do I get if I add those together? Oh, those cancel out. Oh, okay, those cancel out. And so it just gives me a e to the minus 7x. And so, well, for these to match, a's got to be 1. A's got to be 1. A's got, oh, okay, it turned out to be really easy, but I fixed it so that I would give myself a nice, easy question. Obviously, the questions I give you are not nice and easy. So a is 1. So it turns out that a is 1. So our particular integral is just that with a is 1. And so our general solution is going to be, y equals c e to the minus 7x plus x e to the minus 7x. Oh, I might as well combine them together. E to the minus 7x, x plus c. Can I check it? Yeah, but there's a c, there's an unknown in it. Just imagine the c is 1. It won't make any difference. Every time you want to check it and there's a c in there, just imagine it's 1. It won't make any difference. I know when I tell you to put in x to check, I tell you not to put in x is 1 because it's too dangerous. It sometimes comes out as being right when you haven't got it right, because 1 often just ends up giving the same answer whether you have got the differential of it or when you put in x is 1 or whether you haven't. So, but with the c, it doesn't matter. C you can just put in as 1. It'll be fine. It'll be fine. You can still check it. Just pretend the c is 1 and check it. Okay, that's the failure case. Okay, now we need to do one more thing, which is we need to do learn about homogeneous differential equations. So homogeneous, I told you it's a long lesson today. I'm sorry, it's because the worksheet is long, and so I have to cover all the things on the worksheet, so I have to do this bit as well. Otherwise I'd have just stopped there, but it makes sense for me to do this now and cover it now. Okay, so homogeneous differential equations. What does homogeneous mean? Well, do you remember before when we were talking about partial fractions and we said, let's do 4 plus 3x squared over 2 plus x and 3 minus 2x, and we would say that's equal to a over 2 plus x plus b over 3 minus 2x, and then we just do the whole partial fraction thing. It was so much fun, wasn't it?
Cover up.
What's wrong with you lot? Come on, guys, it's the A-level students now. They know these
You can't do that because there is x squared on the top.
It's an improper fraction. You can't do partial fractions if you've got an improper fraction. What's the degree of the top? What's the degree of the numerator? Shruti?
X.
The degree,
I don't know what you mean by
quadratic is degree 2. Any quadratic. 2x squared minus 3x.
Oh, degree 1. No.
It says 4 plus 3x squared.
Oh, what's the degree of that too?
This degree is 2. What's the degree of this
Yeah.
if you multiply it out?
Oh, 2.
Degree is 2. So you can't use partial fractions if the degree of the top is the same.
So you
as
need
2
it to be 1.
It
Okay.
needs to be lower than that, so you're going to have to use polynomial division. Anyway, I only wanted to do that because I wanted you to remind me what degree means. Okay. The degree of this is 2. This is degree 2. This is also degree 2. It's got a y squared in it. This, believe it or not, you're not going to believe it, but it's degree
Degree
3
Oh.
because it's an x squared times a y, which is degree 2 times degree 1. This is
Degree 3.
2 because the
Two.
dy by dx doesn't count as a degree.
Okay.
When you differentiate degree 2, you get degree 1, don't you?
Yeah.
And when you differentiate y, you get dy by dx, but y is degree 1. So if you differentiate it, you have to get degree 0. So dy by dx has to be degree 0.
Degree 2.
So what happens if you take an x and you minus a 2x? What's the answer?
It's a degree 2.
So what I'm
Oh,
asking,
2x.
I'm asking, what do you
Okay.
get 5x minus 3x? What's the answer?
Oh, 2x.
So degree 1 minus
1.
degree 1 is still
But
degree 1.
x and y are different. They're different.
Yeah, but they're still degree 1 each. They're still degree 1 each. So if you do a degree 1 minus a degree 1, you still get a degree
Okay.
1. And then 2 is just a number, so that doesn't count, and that doesn't count. So this is degree 1. So this is degree equals 1. Okay, look at this equation. It's a homogeneous differential equation. Why is it a homogeneous differential equation? Well, what degree is this?
2.
And this?
2.
And this?
2.
So what does homogeneous mean?
All the same degree every
All
time.
the same degree. Homo means the same. Homogeneous means the same type. So, okay. So when we have an equation where everything is the same degree, every term is the same degree, then what we can do is say, well, what is the degree of every term? The degree of every term here is 2. So degree is 2. So what we're going to do is we're going to divide everything through by x squared. X squared. If it's degree 2, we'll divide everything through by x squared. If it's degree 3, we'll divide everything through by x cubed. So we're going to divide everything by x squared. We're going to divide by x squared, and we're going to divide by x squared. And then that's going to give us, well, x squared divided by x squared gives us 1. So dy by dx equals x squared divided by x squared, so that gives us 3, plus x divided by x gives us y over x. Now we're going to replace y over x with u. We're going to use substitution. We're going to replace y over x with u. So we're going to replace the y over x is going to be replaced with u. Okay. Plus 3. Now we can't leave this as dy by dx, because if we did, we'd have 3 variables, y, x, and u. So when we replace the y over x with u, we're going to have to replace the dy by dx. It will force us to replace the dy by dx. But the dy by dx will always be replaced by the same thing. It will always be the same thing. If y over x is u, then y equals u times x. And the differential dy by dx is differentiate this multiplied by this, plus differentiate this multiplied by this. So u plus x du by dx. And it will always be that, so you don't need to work it out each time. If you just memorize that, your life will be perfectly adequate. So the dy by dx has to be replaced with u plus x du by dx. So the dy by dx here has to be replaced with u plus x du by dx. So I've used substitution where u equals y over x. Okay, does that help? Does that help? What I've got now is u plus x du by dx equals 3 plus u. Does it help? Does it help? Does it help?
I'll substitute it in.
Does it help? Does it help? Does it help?
Yes, you can cancel it out.
Cancel out the plus u. Now I've got x du by dx equals 3. An A-level student could solve that.
Bring the x in.
Yeah, du by dx equals 3 over x. Integrate, take the dx up here. integrate 1 with respect to u is u, equals integrate 3 over x is 3 ln x. I'll put a constant inside here. What u stood for y over x. Y over x equals 3 ln ax, and y equals 3x ln a modulus x. There's our answer. Okay, so that's how you do it when you have a homogeneous differential equation. So
so do you need, every time you need to spot whether you've got a homogeneous?
Yeah, but I mean, obviously in the worksheet, what it will do is it will tell you these are homogeneous differential equations, use that method. But obviously
if not, you use the complementary.
Yeah, you know, the worksheet does guide you a little bit. It does say, oh, use this method and use this method and use this method. So it will guide you a little bit because you're just at the learning stage. It's after we get past the learning stage that you'll have to decide for yourself what method to use in each question. Okay. So I don't think we need to do any more examples of that because they're pretty much straightforward. They're kind of self-explanatory. So I'll just give you the homework to do now. Okay, so homework.